And it is my great pleasure to introduce today's chairman, Mr. Stephen Hinchliffe. He is the energy advisory lead of ANZ for Mott MacDonald. He is a fellow of the Institution of Engineering and Technology UK and Chartered Engineering. He has a PhD in power inverter technology and master degrees in electrical and electronic engineering, business administration, and commercial law. He has over 25 years experience in the delivering of strategic consulting services to power network, power generation, renewable and clean energy sectors. He is an active member of Seagrace C5 panel in Australian electricity markets. His expertise include power and low carbon project business case development and options study, grid connection negotiations and compliance, energy market mechanisms, renewable energy project feasibility, embedded generation and total energy management advisory, energy efficiency and clean energy policy development. Stephen supported the Australian government in undertaking an assessment of the impact, including benefits of large-scale hydrogen production on the electricity sector, supporting the World Bank advising on hydrogen value chain for India, a Japanese company undertaking a feasibility study for large-scale green hydrogen production in Australia for export to Japan and Korea, and assessed for proposals for large-scale hydrogen production at a port in South Australia, which is representing up to 9 gigawatts of load, which is quite impressive. Okay, welcome to Stephen, and over to you now. Thank you.
Thank you very much, Lynn. I'm almost embarrassed, almost. So this is the last day. And I'll try and make it a little bit light. Not that I don't take this seriously, but you know, you've got to have fun as well as learn things and talk about things and discuss things. But before I start, I'd like to acknowledge the traditional custodians of the land on which we meet, the Bunurong Boon Wurrung and Wurundjeri Woi Wurrung peoples of the Eastern Kulin Nation, and pay my respects to their elders, past and present. My name is Stephen Hinchliffe, Stephen, and I'm honoured and delighted to chair this last day of the APNA Connecting Green Hydrogen Conference. You will have recognised by my accent that I'm not Australian. Yes? Okay, excellent. I'm a Yorkshireman. And there's one thing to say about Yorkshiremen, well, there's many things to say about Yorkshiremen. One is that there's no point asking a Yorkshireman where he comes from because he'll told you that in the first sentence. Well, I left it to sentence 3. And please do not mention the cricket. It's been a great conference so far, hasn't it? Yeah, I think so. I think it's fantastic. There's been a really impressive range of speakers. And all the delegates that I've met have been well-informed, educated, and erudite. Now, before I get anybody offside, that doesn't mean to say that those that I haven't met are not educated, informed, and erudite. As the Irish say, a stranger is just a friend you haven't met yet. A little bit about my team and what I do at Mott MacDonald, if I may. As Lynn says, I lead the energy advisory business for Mott MacDonald across Australia and New Zealand. I have a team of engineers, energy economists, energy policy specialists, and I support the power sector and industry and governments. And we're particularly passionate about their drive to net zero. Now, I was going to ask for a show of hands as to who's heard of Mott MacDonald. Oh, great. That's more than I anticipated. Well, we're about 16,000 strong globally, on every continent, apart from Antarctica, as far as I know. 2 billion turnover. We're an engineering, economic, environmental, and strategic advisory consultancy. We were founded in 1880. And we developed the first hydroelectric scheme in Scotland in the 1800s. Since then, we've worked on many iconic projects around the globe. We're employee owned, which means that we can drive our own agenda. And as I mentioned, we're really passionate about the drive to net zero. We are internationally credited for being carbon neutral. Now, we achieve this not just by buying offsets, but by actually investing our own money, which is shareholders' dividends, in rehabilitating things like peat bogs in Indonesia. So we're very proud of that fact. Lynn has talked about some of the work we're doing in the hydrogen space. And we've worked on many gigawatts of projects, generally feasibility studies at this stage, of course. And the largest being probably North H2 in the UK, which is one of the largest offshore wind farms to be developed or being developed in Europe, which the intention of which, being H2, is to power electrolyzers. Anyway, enough about Mark MacDonald and me. I should say that the views I am going to express in these opening remarks are my views, and not necessarily the views of my company. That's a legal caveat. We're going through a remarkable change. It reminds me, not that I was there, by the way, it reminds me a little bit of the time of Edison, when he was developing lighting schemes for housing and commercial premises in the US. Or a little bit later, the time when we transitioned from local city-owned power generation and distribution to centralized generation and an interconnected national grid. The drive to net zero is massive. It affects every single aspect of our lives, industry, commerce. It's bigger than Ben-Hur. I remember Ben-Hur, by the way. Charlton Heston? No? Okay. I'm going to be a bit challenging in what I say, and perhaps controversial, all in the interest of sparking debate. And so I'm going to break a little bit with tradition. And during the panel session, I'm actually going to invite the audience to ask questions and not just ask questions myself, because I'm sure you have questions. If not, please start thinking about them. Transition, and the transition that we're going through is not simple, and it is not without costs. There are many interrelated aspects, not least policy, technology, commercial aspects, stakeholder acceptance, social license to operate, and society in general as a whole. We need to think about the fuel poor, and particularly about developing nations and the cost of their energy as they grow their economies. The transition needs to be, and forgive the well-worn word, holistic, in that we need to look at both demand side and supply side. I used to do in a past life a lot of work for the Energy Trust, Energy Savings Trust in the UK. And one of the memorable statements they made was that it's cheaper not to burn a kilowatt hour of energy than it is to generate and deliver it. And that really does hold true today. So efficiency and energy efficiency. And I know we're at a hydrogen conference. Why am I talking about energy efficiency? Well, it all matters. It's all interrelated. It amazes me, coming from a cold climate, that here we are in Australia and we have dark roofs on houses. Go figure. In the Middle East and around the Mediterranean, we learned a long time ago, thousands of years, that you paint your houses white to keep them cool, not dark. There's a lot we can do in Australia and perhaps in other countries to improve the housing stock, to improve overall our energy efficiency, not just in housing, but commercial properties, industry, and the like. And we need to look at those aspects. It is inevitable that energy costs will increase during this transition, at least in the short term. Now, I did read somewhere where the government, and I don't want to be political, but the government says that electricity prices are going to drop by 10%. I don't see it happening. Why? For one thing, taking aside distributed energy resources, if we've got large-scale, centralized, commercial, I should say, and distributed renewable energy sources, wind and solar, and large-scale demand loads like large-scale electrolyzers, which by and large aren't sited close to large transmission lines by their very nature. Electrolyzers will tend to be near ports for export. Then we have to, and as we are, upgrading our electricity network. That costs money. Typically, rule of thumb, about $1 million per kilometer of transmission line. And we need long duration storage. Now, I did a piece of work for a government that I really can't mention, except there's a cricket match being played in the city at the moment. And, all right, it's coincidence. And so they asked me the question, of my team and I, how much storage do we need for different levels of penetration of renewable energy, taking into account the retirement of fossil fuel plant? If, for example, there could be 2 or 3 days consecutive without much production from solar or wind. So maybe being a bit cheeky, I said, well, have you looked at BOM data, Bureau of Meteorology data, to see whether those weather events can happen? Said no. I said, okay, we'll do that. And it just transpires that looking at the past history of data, that you can get on average 2 days, maybe 3 days every 2 years, where there's very little solar and very little wind. So then we looked at modeling this, and okay, just taking it simple, what's the average demand per day, multiplied by 3 times 24 hours gives you the gigawatt hours requirement of storage. And what we discovered was that 75% penetration of renewables, when you've retired most of your fossil fuel fleet, you need enough storage. If you equate megaliters to megawatt hours, that's the top storage in a pumped hydro scheme, you need the amount of water storage equivalent to 1.6 million Olympic-sized swimming pools of water. An Olympic-sized swimming pool holds 2.5 million liters of water. That's 4 trillion liters of storage, which is close to 9 Sydney harbors of water storage. These are big, big numbers. Now, interestingly, the Queensland government has just announced the development of a long duration pump storage scheme at Burrumba Dam, where they've said as part of the specification, it needs to be 2 days of storage. I don't know for sure, but it would be nice if it's a result of them reading the report. Who knows? Can we use hydrogen for storage? I mentioned, or rather Lynn mentioned the work I did for the Victorian government, and I've looked at this. I mean, the answer in Australia, quite frankly, as we generally all know, is no. The cycle efficiency using hydrogen. If you go from electricity to hydrogen to storage, back to electricity, about 14%, maybe 20% with modern electrolyzers. You just wouldn't do it. It's a lot easier to use batteries and pump storage with about an 80% cycle. Doesn't mean to say we shouldn't produce hydrogen. There's a big demand overseas. We've heard that. We've heard that during the conference, but it's not the answer to our storage problems and the problems that are arising. One of the really, how can I put this, refreshing things to me during this presentation, not the presentation, the talk, sorry, and the conference, is that people address the elephant in the room, being the cost of green hydrogen. Now, usually when you read articles on green hydrogen, you listen to talks and you listen to parliamentarians and so on, the costs aren't mentioned, but they have been here and they've been debated, which is absolutely fantastic. Now, we'd heard of figures of about $4 a kilogram, and conveniently expressed by Pedro Descartes in megajoules, because gas is traded in megajoules, So that's $30 a megajoule. Now, by comparison, LNG at the port, exporting from Australia is about $8 a gigajoule. So roughly 4 times the price. At the target of $2 a gigajoule, this equates to twice the price. When I was doing the work for Victorian government, I did a bit of a back of the envelope calculation on what is just the electricity costs of producing hydrogen. Now we've heard from some of the speakers, it's about 60% of the cost of hydrogen. But let's say we connect our hydrogen electrolyzers behind the meter on a solar farm. Solar farms generally need upwards of $40 a megawatt hour, current technologies, to be viable. That equates an electricity cost alone for hydrogen, green hydrogen, of $16 a gigajoule, twice as much as LNG. If you look at wind, you need about $60 a megawatt hour, equates to $24 a gigajoule for hydrogen, 3 times as much. And then if you think about transmission factors, if you connect the transmission line, then obviously the costs are higher, electricity costs are higher. Although there has been some debate about whether the transmission user system cost should be charged to producers of hydrogen. Fine, somebody's got to pick up the cost somewhere. You know, the transmission companies have a regulated asset base and a maximum allowed rate of return. So who pays for it? We do, of course. It's same with subsidies. We pay for it. Taxpayers pay for it. So the point I'm making is transition is not without cost. Doesn't mean to say that we shouldn't go through it. We need to go through it, clearly. You know, global warming is an item. We all know that. Some might argue. Somebody mentioned during this conference about marginal loss factors. And I don't know whether you all know what marginal loss factors are, but basically they're a locational pricing signal to encourage loads close to generators and generators close to loads. So if your electrolyzer plant, gigawatt scale, is remote from generation, regional reference node, then you're hit by a marginal loss factor greater than 1. What does that mean? You pay more for your electricity than you actually use. And the fluctuation in MLFs has had quite a bit of a shock in the renewable sector over the last few years. Not least Broken Hill, for example, where their marginal loss factor as a generator went down from over 1 to 0.7. That's a 30% reduction in revenue. I don't know of any power project that can take a 30% reduction in revenue and survive. So there are costs. So why am I saying this at a hydrogen conference? Because we need to be pragmatic. We need to be honest. We need to have open debate. Because if you don't do that, you can't then galvanize the cerebral mass, if you forgive the phrase, that we have here in the audience and hopefully listening. You know, we've got to know what the issues are. We've got to know what the problems are before we then can start tackling them and addressing them. And we do know from Florence earlier that Germany needs hydrogen to meet its carbon targets. We know that Japan, Korea, and India are factoring large-scale imports of hydrogen. So there is a potential market there. Whether the market can accept the price at the moment is another matter. But then that's for us guys and girls to work out an answer. So we need to be pragmatic, but we need to be entrepreneurial. And if I may sort of coin a phrase, I think we should all become pragmatic entrepreneurialists. Thank you. Oh, thank you for that. Thank you very much. That was interesting. Right, so it's now my pleasure to introduce our keynote speaker, who unfortunately can't be here. And we have a recording of his presentation. Gary just gave me the thumbs up, so I'm right. Nigel Genvey is the Executive Strategy and Growth Initiative Manager at Baker Hughes. He has master's degrees in petroleum engineering and bachelor's degrees in mining engineering. Over 25 years of global energy industry experience in technology, project development, operations with major international companies. He is an industry leader in the energy transition, decarbonization, and carbon management, and an expert in carbon capture, use, and storage. really important if we're looking at blue hydrogen. Nigel has participated and led collaborative industry technology programs, policy and regulatory development, and capability building efforts in low carbon energy. This includes roles such as the chair of several carbon capture bodies internationally, and he's a founding member of the GAIA Sustainability Programme and a peer reviewer for a number of international energy reports. At Baker Hughes, Nigel guides the company's strategy and growth initiatives to advance new frontiers for energy to help meet the global energy demand by offering low carbon solutions. Nigel lives in Houston, Texas with his wife and 2 children. Please enjoy Mr. Genvy's presentation. Thank you.
Many thanks. And it's my sincere pleasure to be virtually with you all today on day 3 of CGHA. I would have loved to have been with you in Melbourne. My name is Nigel Genvy, and I work in New Energy Frontiers at Baker Hughes. The focus of my keynote today is technology innovation, which is at the heart of the low carbon hydrogen revolution. And it's inspiring to see all the progress you are making in technology, policy and finance in the APAC region. Congratulations to you all. The world is watching. I'll be giving you an introduction to Baker Hughes Energy Technology and what we do today in hydrogen and how we are tackling the energy innovation ecosystem. So Baker Hughes is an energy technology company that provides solutions for energy and industrial customers worldwide. With operations in over 120 countries and more than 58,000 employees, we design, manufacture and deliver leading technology solutions for our customers. Powered by the industry's only full stream technology portfolio and enabled by our people and scale, we drive productivity and improve outcomes for ourselves and our customers. From the first rotary drill bit to the world's most extensive portfolio of compressors and gas turbines, and from digital solutions that predict outcomes to modular deep water technology, for more than a century, our inventions have been revolutionizing the industry. We are reducing the carbon intensity of our operations, applying proven low carbon technology to help our customers meet their environmental goals and innovating for the future of energy. At Baker Hughes, we are taking energy forward, making it safer, cleaner, and more efficient for people and the planet. Now, the global energy industry, as you all know, is changing. Experts predict that over the next 30 years, demand for energy will continue to grow by as much as 30%. There will be a higher demand for renewables and natural gas, but oil will remain a big piece of the energy mix too. As I said, Baker Hughes is an energy technology company. Our technology and service offerings uniquely position us for opportunities created by the energy transition. And by anticipating future energy needs and trends and leveraging our unique product mix of oil field, turbo machinery, measurement and digital solutions, we can make energy cleaner, safer and more efficient for people and the planet. We aspire to make Baker Hughes the provider of choice in the energy industry of the future. Now, the core of our strategy is to operate strong, market-leading product companies that are best in class in their industry segments. Our product companies meet the needs of customers today with innovative technology solutions, excellent service and quality, and competitive cost structures. We're investing for growth in high potential segments where we have a strong position. And over the long term, we're positioning for new frontiers to capture the opportunities created by the energy transition. Now, we get asked a lot about how we continually innovate. Industrial and digital technology leadership is core to who we are. We apply engineering, science, and data to redefine really what's possible. We put our entrepreneurial spirit and our history of innovation to work every day. Our original thinking and practical know-how drives our technological advantage and global capabilities. With more than 3,066 patents, Baker Hughes holds the most oil and gas technology patents of any company globally. To date, we've invested over $595 million in research and development and introduced more than 100 new products. Our innovation agenda is driven in 4 key areas. Our innovators, our global network of 9,000 engineers and scientists, which I'm very proud to be a part of. Our industrial innovation, enhancing productivity for ourselves and our customers through streamlined manufacturing and supply chains. Digital innovation, delivering enterprise scale AI and intelligent automation across the value chain. And new technology and ventures, and that's where we explore new ways to adapt, apply, and iterate new technologies and accelerate them to the market through partnerships like Avitas and Nextstream. So in digital transformation, we work to deliver enterprise scale AI across the value chain and drive that intelligent automation through the integration of emerging technologies. Our goal is to augment the way we interact with data and machinery at the source of the operation, and that will enable our customers to make quick, accurate, and predictive solutions. Our digital strategy is based on 3 core competencies. Firstly, edge computing. Now, we believe that only a company with more than a century of expertise that understands the equipment, the processes, and people at the edge where data originates can support and accelerate the comprehensive change required for digital transformation. And second, implementing enterprise scale artificial intelligence. Our leadership in the AI comes from the Baker Hughes C3.ai joint venture, bringing together 2 experts in their respective domains. C3 brings a leading platform for scaling AI applications, while Baker Hughes brings deep competencies in services, advisory, and experience with delivering digital solutions at scale. And thirdly, driving a step change in intelligent automation. While there are varying approaches to digitalization, we believe in solutions that use data to improve key operational challenges, such as reliability, productivity, and safety. Now, in the energy transition, our approach to low carbon energy also has 3 parts. Firstly, reduce the emissions from our own operations. Now, we've publicly committed to reduce carbon equivalent emissions by 50% by 2030 and to achieve net zero equivalent emissions by 2050 to align, of course, with the Paris Climate Agreement. Over the last 7 years, we've reduced our carbon equivalent emissions by 31%, demonstrating our commitment and giving us a chance to build our in-house knowledge and expertise in low carbon energy. Secondly, to put our existing technology to work today, helping the industry take immediate action to control and reduce emissions. We are actively engaged in low carbon projects with many major multinationals and national oil companies today, and of course, more on the horizon. And thirdly, to invest in the development of new technology that will secure our leadership position in low carbon energy technology. This will come through a combination, of course, of both in-house research development and partnerships and new ventures. Now, the challenge of the energy transition is the implementation of new technologies at the scale and pace needed to mitigate the worst impacts of climate change. And we see really 3 hard truths. On the left-hand side of this slide, you can see they are acceleration of action in existing and new forms of low carbon energy. It's critical, but it will not meet the scale needed. Secondly, oil and gas production is therefore part of the mix. So efficiency to reduce emissions is a major key. And thirdly, energy producers, technology and service providers, energy buyers, policymakers, and the community at large, they need to come together to achieve our collective ambitions. There is no net zero without partnership and collaboration. And on the right-hand side is a color-coded depiction of the IEA, where they predict the contribution that new technologies, being the white and the light green squares, being a total of 75%, will have to the total emission reductions needed to meet net zero by 2070. Partnership and collaboration in new technology is therefore the cornerstone of net zero. So it's about time I spoke more about hydrogen specifically. And as you can see from this slide, we cover all elements of the hydrogen value chain. As I mentioned, we've almost 60 years of experience working with hydrogen. We develop technologies in hydrogen production, transportation, and utilization segments of the value chain that include our existing range of compression, expanders, pumps, and gas turbines. Compression systems needed to be able to follow 0 to 100% hydrogen flows within a few hours. Now, of course, not all technologies can do that, and control system design is key, as well as mechanical ability, of course, to follow the ramp. On gas turbines, systems need to be able to handle variable hydrogen blending. And we're also developing capability to support applications for mobility, be it in forklift trucks, passenger vehicles, heavy-duty road transport, rail and ship, and exploring what other elements of the value chain is worthwhile. We also have a lot of experience in hydrogen, thanks to continuous investment throughout the years and our experience acquired in downstream oil and gas applications. We therefore aren't newcomers to the hydrogen space. In fact, our experience in the treatment of hydrogen began in 1962 with the first hydrogen compressor with Nuovo Pignoni. With gas turbines in 2008, we built the first turbine in the world. It's a 10 megawatt power to run on 100% hydrogen at the Fusina Hydrogen Power Project in Italy. In both compression and gas turbines, our technology therefore is well proven. We have more than 2,000 hydrogen compression units installed across multiple applications. With our gas turbine technology, we have an established experience in burning a variety of fuel mixtures with hydrogen content, from 5% up to 100%, including about 70 projects now worldwide using frame and aeroderivative gas turbines. We've extended the capabilities of our new Nova LT gas turbine generator technology to start and operate on 100% hydrogen fuel, as demonstrated by the successful completion in July 2020 of the combustion test of our new 16 megawatt hydrogen turbine with Snam, an Italian energy infrastructure company. And our high pressure ratio compressors provide significant advantages for green hydrogen projects. Here, this slide, of course, shows our high pressure ratio compression advantages. They include up to 50% smaller footprint, up to 30% lighter weight, simplified installation, higher reliability, higher availability, lower downtime, lower total cost of ownership, and that wide ramping flexibility. Now, our hydrogen-fired gas turbines are available today, and we have over 70 projects in place, as I said before. And importantly, this includes our Nova LT turbines, which are able to start, as I said, and run on 100% hydrogen. Now, the role of gas turbines in energy transition can become critical with hydrogen fuel capabilities. Mixing renewable gas, i.e. green hydrogen, biogas, syngas, with natural gas enables further reduction, of course, in CO2 emissions. Gas turbines are flexible, they're well suited for frequent starts and able to provide fast response to grid demands, making them really what is a perfect partner to the intermittency associated with renewable power from wind and solar. So I've given you an introduction to Baker Hughes Energy Technology and what we do today in hydrogen. Let me now take you through how we are tackling the energy innovation ecosystem. Now, as a global energy technology company, we're committed to continue innovation, to advance, scale, commercialize a range of technology solutions to reach net zero ambitions. And as you know, we're not new to energy. I mentioned that Baker Hughes has been in the hydrogen space since 1962, and we've also been in the geothermal space for about 40 years, and in the carbon capture and utilization and storage space for way more than a decade. But technology advances continue in these areas and also in other low carbon energy technologies. So we also have cross-company teams that continually inventing, incubating, developing, and commercializing new technologies, both from an organic and an inorganic sense. So let me give you an overview what the scale and scope of clean energy or climate tech innovation ecosystem is. So as the IEA, the International Energy Agency, have shared in their recent special report on clean energy innovation, to meet net zero climate targets by 2070, we will have 25% of the GHG emission reductions will come from technologies currently available. That's a technology readiness level of 11. 40% will come from technologies that are not yet commercially deployed. That's a technology readiness level of between 9 to 10. And 35% will come from technologies in the prototype or demonstration phase. That means technology readiness levels of 4 to 8. Now, let me tell you what those different TRLs, technology readiness levels, really mean in the process of maturing a technology. So TRL 4 to 6, that's prototyping. A concept is developed into a design and then into a prototype for a new device. Of course, that's also known as research and development phase. Technology readiness levels of 7 to 8, that's demonstration. That's their first examples of a new technology being introduced at the scale of a full-scale commercial unit. Now, the next two categories represent deployment. So that's TRL 9 to 10. That's early adoption. At this stage, there is still a cost and performance gap with established technologies, which policy attention must address. This is about moving from first of a kind, FOAC, and incorporating learning by doing cost reductions and performance improvements. And then lastly, TRL 11, that's mature technology in deployment. And as, of course, that deployment progresses, the product will move into a mainstream as a common choice for new purchases. Cost reduction will continue through optimization, large-scale manufacturing, and of course, supply chain cost improvements. And to categorize the startup world, venture capital spend in clean tech has progressively increased year on year to a total of now about $328 billion and spanning across 13,500 deals in 2020. The average deal cost has been increasing at about a CAGR of 11% over the last 4 years. Now, that's impressive. However, only $15 billion or 5% of the capital invested is on early stage technologies. And as I said before, 35% of all GHG emission reductions to achieve net zero by 2070 come from those early stage technologies. So to enable a hydrogen economy, we need to cooperate in the development of technologies. We're faced with various problems today. Not all technologies are available, as I've just said. Innovative business models are needed to address some of the economic challenges. We need ways to support and accelerate technologies through the valley of death. And risks of new and nascent markets and technology adoption need to be managed and minimized. So our solution to this is to really bring pace to technology demonstration and deployment, providing a safe space for ideas to grow and flourish, help our customers deploy net zero technologies safely and efficiently, and lastly, drive consistency and quality in technology development. So here's some great examples of our existing investments and partnerships in low carbon energy technologies. And we're constantly looking to find new collaborations. Now, I'll give you some more color on what we are working on with SNAM and Air Products. So in July, Baker Hughes, together with SNAM, and as I said, Italy infrastructure developer, and actually Europe's largest gas network operator, completed the testing for the operation of the world's first hydrogen turbine designed for a natural gas transportation infrastructure. That test paves the way to implement the adoption of hydrogen blended gas in the current infrastructure, thanks to the Baker Hughes LT12 gas turbine technology. So the Nova LT12 will not only help to compress and move hydrogen fuel blends through SNAM's transmission network of pipelines, but the turbine will simultaneously use the same fuel to power itself. And in June this year, Baker Hughes, together with Air Products, a global leader in industrial gases and a mega project developer, announced a strategic global collaboration to develop next generation hydrogen compression, lower the cost of production and accelerate the adoption of hydrogen as a zero. Now, as part of that collaboration, we at Baker Hughes, we're going to be providing Air Products with hydrogen compression and gas turbine technology for global projects, including the advanced compression technology for the NOAM carbon-free hydrogen kingdom of Saudi Arabia, and our Nova LT16 turbines for Air Product Zero Hydrogen Energy Complex in Edmonton, Alberta, Canada. So I hope you found a useful introduction to Baker Hughes as an energy technology company, what we do today in hydrogen, and how we are tackling this wide energy innovation ecosystem. The low carbon hydrogen economy is starting to take energy forward, and we are proud to be a part of the future in making energy safer, cleaner, and more efficient for people and the planet. Have a great day 3 of the conference, and I wish you all great success. Thank you.
A very illuminating presentation. We're running about 10 minutes behind schedule. We started 10 minutes late. So what I may do is cut down the break period a little, see how we go. We're now moving on to the technical box plus Q&A, entitled Advanced Projects and Technical Update. We'll first hear from Karen Bagger of ThyssenKrupp. Did I pronounce that correctly? Thank you. on the evolution of ThyssenKrupp's Under's large-scale water electrolysis and green chemicals technologies. Karen has a postgraduate degree in chemical engineering and is a chartered engineer with IChemE. He has 21 years of experience in the process industry, spanning the energy, hydrocarbons, petrochemicals sectors, including the development of renewable energy applications. Karen is the Chief Technology Officer, train these teeth for a donkey, I know, of ThyssenKrupp, and heads up the company's Green Hydrogen and Chemicals Technology Division in Australia. Karen is responsible for furthering and strategic implementation of technologies such as water electrolysis. Karen has expertise in technology development, design, optimization, and operation of hydrogen and ammonia value chains, and carbon capture and use, very important for blue hydrogen. Please welcome Karen Bagger.
Thank you, Matt. Stefan, first of all, thank you, and also the Leaders Associates for organizing this wonderful event, and all the audiences that have turned up here despite the bad weather. I myself nearly forgot to do that. Nevertheless, I think we've heard some really good talks over the last couple of days, and specifically in the policy and the trade aspects of the green hydrogen value chain, and also what's needed here in Australia specifically for progressing the industry further. Today I'll talk about the technology development at our end and bring the rear end to enable this industry, and also talk about the continuous innovation that we are which underpins our product offerings. So without further ado, let me kickstart. So my presentation essentially today will just be over 3 parts. In essence, let me go here. So we'll talk about the vision that we have for the green hydrogen economy, and let's keep going. And what we see, where we see the drivers coming from. Then we will talk briefly about the industry and areas to focus. Doesn't want to stay there. And the last part of my presentation will go a bit deeper into the areas that we are focusing on and innovating in our state-of-the-art powder-to-X applications. And technologies such as fertilizers and enabled by the green ammonia and green methanol technologies. So first of all, let's look at the vision that we have. So we have both sides of the overall value chain. So we play on the supply side, which is on the right-hand side, and also on the market side, which is as virtue of our steel business. The market and the supply enablers. So we've, as a result of that, we've set about 30% CO2 reduction target by 2030 in our steel business, which then enables also the development of our own technologies to not only achieve that for our business, but also for large-scale deployment in the industry that we already play in, which is the heavy chemical industries and the conventional hydrogen technology. To give you a bit of a background, where are we placed in the hydrogen value chain? I wanted to take the opportunity to present the overall pictures of our perspective. And here in this case, if you look at the left-hand side here, the renewable power where hydrogen itself is not applicable, that's basically to drive the decarbonization, electrification of everything before turning into hydrogen or turning into molecules is essential. I think everybody agrees, and there's no doubt about that. And then, of course, from there onwards, the grid itself has to be ultimately made suitable for large-scale movement of electrons in the grid. For, of course, if we need to decarbonize at a pace. But in the center sits the green hydrogen, and why that's important here in this case is that it forms an enabler between what we consider is the largest driver for a fast deployment, that is the industry sector. So in this case, we've already got several use cases for what we call, let's say, gray hydrogen or conventional hydrogen, being fertilizer or steel industry, And here that serves as a ready sink for large-scale deployment of and use case for green hydrogen or renewable generated hydrogen. But what's even more interesting in this landscape is the role that hydrogen plays, and I think we've heard about that before as well, is plays in connecting both the renewable side as well as the chemical. So on the downstream side, it is obviously a feedstock, and that's where a lot of our technologies are currently deployed in the world. But on the upstream side, it also plays as a key enabler for large-scale deployment of renewable generation by providing flexibility, load balancing, and also grid frequency control services. So this is quite a unique characteristic, which is not typically the case in the chemical industry. Typically, natural gas-driven chemical industries, get the gas out of the ground, and of course, it's a push system. Essentially, serves just the downstream chemicals. But here, this reflects an opportunity as well as a challenge. And I think today we'll talk a little bit about the challenges and how we're trying to turn that into opportunity by continuously innovating our own technologies. So let me first go into why we consider that the industry sector is the key driver. So as I mentioned before, there's already globally about 600 gigawatts worth of hydrogen. If I was to convert that equivalent into 100% capacity factor-based electrolysis capacity, that is currently produced. Only about 4% of that is renewable hydrogen. And a lot of that is actually in the in the chlorine industry, where hydrogen is essentially a byproduct or turned into chemicals, which we use on a daily basis. However, never really consider them to be the primary, let's say, the products that we need to decarbonize. And I'm talking here acid, hydrochloric acid, for example, or bleach. The second aspect or second driver for green hydrogen here is of course, for large scale industry applications such as ammonia plants, as I mentioned before, the downstream aspect is already quite exists in large scale. So, the 3,500 ton a day plants today exist. And to match that, we need an equal size renewable generation or renewable hydrogen generation, which leads to over 1 gigawatt of electrolysis. So therefore, again, for the new plants and also for the revamp or hybrid revamp of the existing ammonia plants, electrolysis or electrolytic hydrogen serves as a good replacement. The third factor we think is key here is, of course, there is immense cost pressure. We've heard Stefan just talk about before cost of making hydrogen, and that is the elephant in the room, I think has been for a long time. And here we think that the scale up, again, due to the previous two reasons I mentioned, provides a unique opportunity to continue bringing the cost down. And you can see that here, a 2 megawatt system, which is fit for perhaps mobility applications, and going down to a gigawatt system, you're looking at a cost decrease of close to 70 to 80% if you talk about specific cost decrease. And the fourth and perhaps most important aspect here, if we were to talk about hydrogen being a global industry and traded industry, is that we need to move it around the globe. Moving it around in small ships, of course, is going to hurt the economics. So here too, to make it in large scale, to move it in large scale, and ultimately get the scale benefit throughout the value chain, it is important that that the large scale technologies are deployed soon enough. Yeah. So this picture shows, again, our vision and essentially some of the key technologies that we offer in this space. So I'll start on the left-hand side. Of course, in the carbon emitting industries, we still got to treat carbon as a useful commodity, as a feedstock. We cannot imagine life without carbon. It's just that it needs to be the right kind and right form. Yeah. So of course, the CO2 emitting industries here, we do have technologies here that we offer for capturing the CO2 and turning into valuable chemicals. In this case, be it fuels, methanol, synthetic natural gas, which has perhaps a more decentralized use, maybe more in Europe, less so in Australia. But in Australia, we see definitely use cases for methanol, and of course, the champion here being ammonia, yes, but doesn't need carbon, of course. These are the key downstream technologies that are enabled by large-scale electrolysis, which I'm going to talk about today. And on the downstream side, you can see a number of applications which range from fuels, steel, making, which we've heard a lot about recently, and of course is a fantastic opportunity for Australia to dive into that industry. And of course, the chemical and fertilizer industry, which is, I would say, perhaps the mainstay. Having looked at or having studied the industry the last 5 years, I would say, presents the best case opportunity for us in Australia to do that, and generally in APAC. So let's demonstrate this via a use case. So here I've got, I'm just going to put up ammonia value chain. So here, ammonia as an energy carrier. This is, so of course, making ammonia via electrolytic hydrogen. I think we all know about that. Generally speaking, and then moving that hydrogen across our oceans to perhaps more power-hungry nations from here, such as Korea and Japan, and then either using it directly for direct as a feedstock or a power source, or in fact even cracking it back to hydrogen. So as compared to liquid hydrogen itself, the disadvantages, most people would be aware of that, is of course the liquid hydrogen movement is an unproven technology at the moment. It is very lossy, which hurts the economics at the end of the day. Of course, we also heard about the efficiency of power to X, and I quite fully agree with that, the fact that transition have to have a cost. But it is also about economic efficiency, not just the efficiency that we engineers perhaps think of in general sense, thermodynamic efficiency. I consider more of it being an economic efficiency. So ultimately, the best cost solution wins. And the best cost solution here is not necessarily going to compete with the incumbent solution. That is the whole reason we are doing this today. So that the incumbent solution is causing issues. I think talking about the challenges will be incomplete if we don't understand the actual problem. So I'd like to demonstrate it via just some basic studies that we've done, and also share with you how that then provides us a guide rail for focusing on our technology development. So most of you would be familiar with this. So here I'm choosing, of course, an ammonia plant, or renewable green ammonia plant as an example. The breakdown that you see in the pie chart is, or donut in this case, is the different contributions of different aspects of the plant or overall project development to the cost itself. So you can see here, what comes to mind is the overall power consumption. And this is a large scale plant. I'm talking several thousand tons a day. Power consumption dominates. So power cost actually dominates in this case. But we simply understand power contribution as mainly related to cost. Of course, is the biggest factor. We have to pick one thing, it will be this. And then comes, of course, the cost of the plant itself, cost of building it. In Australia, that's not cheap, and that could vary as well. You can see that water costs are marginal in this case. Most people think water is perhaps more a sustainability issue, but not a cost issue. And then the overall O&M. So let's take a quick look at what else matters. So power cost, that is the biggest driver, as I mentioned. However, there is still the subset of the power, or hidden within the power, cost related to the power is the process efficiency, be it for conversion, energy, and exergy essentially is the quality of the energy to minimize the wastage, and of course the effective utilization of the plant. Power cost could be really cheap, but if you don't utilize the plant properly, of course, it's going to, again, penalize the economic. Next comes the cost of the plant. Of course, there we can tackle that with building large plants, smaller hydrogen storage in this case, and standardization as much as possible. Yeah. Construction, again, in a place like Australia, this is also be expensive. So here the ease of construction would come into play. Modularization to the extent justified would also be key here. And of course, again, standardization to the extent. Last one is quite interesting. Actually, when you look at it, it's less than 10% overall operating and maintenance costs. Yeah. So, and here you think about the general things being, automate as much as possible, low maintenance, be it for electrolysis, for the ammonia plant, or even the balance of the plant would be key here. But one thing I'd like to point out, this is the O&M cost if you do it properly. The cost of not maintaining the plant, or let's say a plant that is not maintainable, is extremely high, because it not only just costs you money, It also costs you downtime and loss of production. And this pie or piece of the donut will grow big time. So it is important that when we talk about the actual deployed plant, that it is maintainable and very reliable, so that ultimately it is able to fulfill its job, which is to make hydrogen or ammonia in this case. So please keep these 4 things in mind, because throughout the presentation, you will see themes of this in our technology development. Let me start with the electrolysis first. So many of you probably know us from the chloralkali industry. So ThyssenKrupp has over 10 gigawatts of installed electrolysis capacity in the world today, and that's about 51% of overall chloralkali market share. So if you consider the equivalent and all of those plants are actually making hydrogen, of course. And that's our experience spans over the last 40 years or so, and having deployed about 600 plants, about 40 of them EPC. The overall cell making capacity in our factories is over a gigawatt a year. Precisely, it's about 1.2. The cells that are made, so electrolysis itself, you can see our current module, which is the largest module, single train module in the world. It is 20 megawatt nominal capacity, and is actually built up of from the single most, let's say, atomic level being at a cell level. So one of the unique things about our alkaline water electrolysis is that it is actually isolatable to a single element. Means that you have all the stack itself consists of close to, say, 300 cells in a 20 megawatt system, which allows them to operate quite independently to each other. And this is a lot for maintenance, as I mentioned before. These cells can be maintained individually. You can remove it if need be, if it's faulty. To shut down you have to shut down the stack to remove it, but you don't have to replace the whole stack and find a problem here. Of course, being a low pressure alkaline water electrolysis, so these units run at about 30 kPa. Of course, we'll need then compression downstream depending on the end application. But these features then allow us to improve, let's say, the overall availability of the plant being a low pressure operation. It's fairly reliable, and of course there is a lot less material. These features, as I mentioned before, so again, being a single cell design is very critical for high availability, low downtime, and low mean time to repair. Actually. Of course, one other thing I forgot to mention here is the dynamic aspect of our advanced electrolysis, really quick, and has actually been qualified for primary reserve in Europe. Yeah. Now we're looking at the actual technology improvement. So we've taken 2 paths here. So the process intensification, and that's by way of improved electrochemistry, active catalyst, and improved membranes. So this has continuously improved over the last 3 years. I would say that I've seen 3 versions of our own offerings. So on the right-hand side, you can see the 10 megawatt was in 2019, and a 20 megawatt module in the end, as it was at the beginning of this year. So the essentially has dropped by about 30%, 30 to 40%. And of course, you can see that here, along with that comes CapEx, because there are a lot less number of cells, but you get double the capacity. And of course, a lower O&M as well, because there are, again, a lot less number of cells that have to be. Again, I'd like to mention here that these units at the end of the life, which is, say, let's say 8 years, considering full load hours, where the stack, essentially these cells, because they are at a cellular level, effectively get refurbished and sent back. Yeah, so this is something that we can do. We offer this service and even would lease the cells to you. So it's not a fixed CapEx the project has to bear. It's a little bit more focus on on specific areas of development. So cost reduction for execution purposes. So again, semi-serial production in the construction yards. So standardized shipment in containers, predefined engineering. Of course, if we have to do repeated deployment, it would make absolute sense to standardize these to the extent possible. Yeah. Then we come and look at the balance of plant aspects. Again, here it would benefit a lot from the overall scale and the harmonization with the power electronics in this case. There can be stray currents in the electrolysis, and hence you cannot just continue to add cells or make them bigger and bigger. They need to be perfectly in sync with the transformer rectifier, and hence there is a practical limitation of how big they can grow. But electrolysis reaction itself is an area-based reaction, as everyone knows, and that in essence means that making the area larger would make it more efficient to the extent possible, as long as the current density is in the right optimum range. In the stack itself, we, again, as I mentioned, the area, of course, matters. The material, that's one of the inclusions or reasons for high cost. Reducing that over the time or over the generations definitely helps. And then manufacturing, high volume and automation. Yeah. So I just want to highlight quickly the benefits of a single cell design here. Just to put this in perspective. So on the screen that you see is the older generation models in the blue line, where it's followed its technology development cycle, but the new generation comes in and can be with full backward compatibility, such that they can retrospectively go into the existing units to bring about the benefit to the clients and the customers. And this has been done and proven in our chlor-alkali industry. So we intend to carry this fully forward into the hydrogen industry as well. Of course, the benefit of this, just to pictorially look at this, that due to the improved efficiencies of the catalyst, it manifests itself in either increased hydrogen production or decreased power consumption here. And this delta here would really depend on the timing and also the maintenance and schedule. From there onwards, just quickly looking at the actual fabrication aspect to this, of how these plants are modularized and put together to make up for larger size plants. So today we have concepts available from 20 to 2 gigawatt systems, and essentially a bulk of that is, by simply numbering up, that can be done. However, integrating it with the downstream chemical side is where the challenge comes, and I'll get into that in the next couple of slides. We target 5 gigawatts of fabrication capacity annually by 2025. This is our goal and our vision. And this is underpinned by our ongoing developments at Carbon to Chem technical centers. This is essentially the test bed for a lot of our technology developments. Before I jump onto ammonia very quickly, I'd like to mention these few key projects that we are currently busy with. Of course, the key one here being the NEOM project. That's a 650 tons a day of hydrogen production. That's where the electrolysis is being supplied. Looking at the downstream side for ammonia now, again, a very similar experience exists. Overall production of ammonia today in the world is around 150 tons a day, 150 million tons per annum, and about 50 million ton of those, that ammonia is made by ThyssenKrupp plants today. Here too, of course, pairing up with the upstream side, as I mentioned earlier, what is really important is the flexibility of the downstream plant and how the plant is able to handle the overall harmonization with the upstream hydrogen generation. So in this case, of course, we have patent pending our current offerings for high flexibility plants that we are currently offering for smaller scale plants ranging from 50 tons a day to 5,000 tons a day, single train designs. And one of the key features here is, of course, the digitalization and harmonization with the weather forecasting systems. But key aspect here for some of the keen engineers I'd like to mention here is that this is done without pressure change in the system. And this is critical for, again, longevity and safe operation of the ammonia plants. So in terms of some experience, again, very large scale plants built. The 5 largest plants in the world are ThyssenKrupp plants. And actually just 2 days ago, we've commissioned and made first ammonia in the plant in the middle, which is in Brunei. It's a 2,200 ton a day conventional ammonia plant. Right, down to the last 2 slides. I wouldn't be completing this without talking about the other aspect or other end of the value chain, which is ammonia cracking. So ammonia cracking itself, of course, is nothing new, but it hasn't been done at a scale that the industry demands now. So in this case, the cracking aspect, when again competes with liquid hydrogen, I mentioned, but you can see some Sankey diagrams on the right-hand side to just show quantitatively what it means when comparing with hydrogen. You can see that the ammonia is still marginally ahead in that sense. Of course, the efficiencies are low. What we are comparing here, apples versus apples, as opposed to comparing it with absolute efficiency numbers. And in this instance, we are developing large-scale cracking solutions. In fact, today we do offer concepts and would be very keen to talk about any commercial projects that you're thinking about. We have partnerships with some key catalyst suppliers, and overall looking at building plants of more than say 300 ton a day ammonia to up to 2,000 or 3,000 ton a day ammonia cracking solutions with an overall efficiency of around 75 to 80%. That's a conversion efficiency. I'll wrap it up now with just last slide. Again, just the final message here that this overall deployment of the, let's say, Power-to-X industry here is a confluence of the right technology, which has to continuously innovate. And even though the 2 key aspects of Power-to-X, mainly industry being hydrogen generation and conversion, are well proven together, there will be some aspects of that will be new. So here, the right partners have to come together, and having a full view of the overall integrated value chain really helps to focus on the areas that do matter here. And in this case, ultimately, it's a compromise of flexibility and rigidity, and we think we have the technical solutions available, and we would be welcoming any projects that get to a point where these can be deployed. Thank you very much. No, if you can't. We are running out of time, but if anybody has one question that would like to ask,
Thank you. I just got a question for the hydrogen electrolysis. I'm just wondering if it is used like a kind of long duration storage system to supply the power system stability, like doing FCAS market. Is that possible to do like a FFR, like a fast frequency response? What is the time interval, like a 0.2 second? And
yeah, so normally I think if you ask a general question that can electrolysis systems do it, of course the answer is yes. I think we have if you already deployed examples. With respect to our offerings, of course, as I said, our AWE is actually qualified for primary reserve. This is independently qualified in Germany, which means that they are qualified to provide that grid stability services. It really does depend on the standards and location, where sometimes the ramp time required is quite stringent, in which case some specific considerations would apply. But to answer your question, yes, they can be done. We have that qualification for electrolysis. The ramp time would range from anywhere between 30 seconds for a full 10% to 100% to around 3 to 4 minutes. It's really a case of what you're willing to pay in the end to do that or achieve that. But that's the range we offer.
Our next speaker is Tyler McCurtich of Endress Hauser, Australia. And he'll be presenting on best practices in monitoring and controlling hydrogen processes. Taylor is the industry manager focusing on mining, metals, oil and gas sectors in the Endress Hauser Australia group. He has extensive experience in the heavy industry processing sector, focusing on process improvements, operational excellence, and engineering improvement solutions. Building on a little thing from what Karen was saying about it's very important to maintain your kit, as it were. His team have worked on several hydrogen projects over the last 5 years, both in Australia and overseas. Taylor specializes in applications in hydrogen processes and he and his team are always looking for different ways to apply the latest technology to bring value to the hydrogen process. Please welcome Tyler McCurtich.
Thank you for the introduction and good morning to everyone. So I'm going to be speaking around Endress and Hauser and how we can help assist operations, technology providers and OEMs around monitoring and controlling their hydrogen practices. So a bit about Endress and Hauser. I'm not sure if you have all heard about us before, but we are a family company founded in 1953. And for our customers, we act as a global partner who can be relied upon around the clock and around the world. The majority of our earnings flow back to the company as a privately owned family company. And as a result, we can invest a lot of funding into R&D. So you'll see we've got more than 8,000 patents and patent applications there. With a workforce of coming up to 15,000, we make sure that we do invest a large number of funds towards the R&D. So last year, we invested over $200 million in R&D. In terms of globalization, we know that innovation is an important driver of our business as well. So where we are around the globe, so we have a holding company in Switzerland, and we have lots of different production facilities around the world. We have sales centers and representatives in over 120 countries, and we also have a regional support network. And as a business, we have committed to net zero emissions as well. And as part of that, we're focused on allocating a lot of the R&D funding towards products that have very high standards for the process environmental safety as well. And as a result, we've been focusing on our product portfolio that supports online measurements and quantity and quality parameters in the hydrogen production, storage, transportation, and also end-use processes. And as a result, we're also making sure that we do invest in people, products, services, and solutions for these innovative industries. Now, as we know, and we've been hearing from the last few days' presentations and panels, that there is a lot of key drivers for why we're heading towards hydrogen. And some of them are listed here on the slide in front of you. But after years of discussion, I think we can all agree that hydrogen is finally at that tipping point where we're crossing the chasm towards a final solution for that. And a part of this is the technology side as well. So as we head into the future, the economics of the technology will become more and more favorable. And as a result, our business as well has realized this, and this is why we are also adding a lot of capability and resources dedicated to the sector. On the next slide here, you'll see that this is our view of the hydrogen ecosystem. So we've had a number of different businesses express their views around the hydrogen ecosystem. And here it looks quite similar as well. In terms of the different types of hydrogen that we have experience in, so historically it has been around the gray and the blue hydrogen, but increasingly we're seeing the technology and the projects come online around green hydrogen. So At the moment, we know that hydrogen use today is dominated by industry, namely in Europe around oil refining, ammonia production, methanol production, and also steel production. And at the moment, a lot of the projects that historically we have been implementing our devices into is that it's been supplied from fossil fuels. So there's a large potential of emission reductions for this type of clean hydrogen. In transport, buildings and power generation, that's also an area where we're seeing an increased focus around the different projects. Now, what else do we actually do in terms of hydrogen? So we provide a portfolio that gives information around the quality, quantity, and composition of hydrogen itself. So whether it's in a production process, whether it's in the storage of hydrogen itself, the transportation, maybe at the point of sale, and also utilization, we have devices that can tell the quantity, the quality, and the composition of that. In terms of our more traditional instrumentation portfolio, so these are some of the type of the devices that we can deploy so that you can monitor or control your hydrogen application or process. So from the flow of the gases and the liquids is all deployed in the production, the level of tanks, the pressure, which is important for hydrogen production, temperature, and liquid analysis portfolio. All these instruments add value to operations that are trying to optimize their process. In alkaline electrolyzer, for example, we've customized our flow portfolio to ensure that it's robust and also reliable in electrolyzer applications. And here's an example from a recent project that we had in Germany. This particular alkaline electrolyzer was powered by wind and also spare hydro power that they had in that area. And you can see a few pictures there around some of the devices that we've implemented. So the temperature in the process, and then the magnetic flow as well for liquid electrolyte. In terms of measuring water quality for the electrolysis, we know that it's quite important to make sure that the water quality is a very high level to increase longevity of electrolyzer membranes and also increase efficiency of the plant. So this is quite challenging traditionally for instrumentation to detect the low level of conductivity in the water. And this is where you can see some examples of the RO skid on the right-hand side with our instrumentation to detect that conductivity level and also the high pH that would be experienced in alkaline electrolyzers. And of course, we're dealing as well with very high purity precursors as well. In terms of the output of an electrolyzer or a hydrogen plant, there's three main areas where measuring of the quality and the quantity is really what we see in projects coming up. So the first of all, we see that it's important for operations and customers and providers of the technology to measure custody transfer and also have information around mass balancing. So that first picture down the bottom there is an example of a custody transfer hydrogen skid, where we have very accurate devices that can measure the hydrogen being deployed at the point of sale between different customers, and also to ensure that the mass balance of the plant and the process is as accurate as possible. The second picture there is around trace moisture detector. And also we see other quality measurements that are important. Now, it's important that the solution that we provide is compact and there's a low cost of ownership. As mentioned before, maintenance costs in these plants, it's important to make sure that they are low. because there is going to be a large economic price to a customer if, or a process if the quality measurement is not available. And finally, the third picture there is an example of getting calorific value from the hydrogen produced, as well as composition for blending purposes. So if you're blending hydrogen into a natural gas line, for example, and you want to determine that the composition of the gas, then something what we call the optograph, which I'll get into in a few more slides, is the best solution for high performance fuel blending. And it's that last device that I want to dive a bit more into detail around, just because it's so unique. And so it brings a lot of benefits if you do measure your composition of your hydrogen stream. Now, what's really so special about this technology? So I won't go into too much detail here, but really what it is, if you can think back to your physical chemistry days, is that the gas sample is activated with a laser, and this laser is of a certain wavelength. When the vibrational energy states of the different molecules, when they relax, then you get Stokes-Raman scattering, and this emits a different light depending on the molecule that has got that spectra. So you can see that we use a green laser, and then out of that, there's lots of different colors. Those colors are then added to a analyzer, which then displays the spectrum compared to the composition of the gas. So you can see there on that slide. So the best thing about this device is that it has a simple spectra that allows it to use a method-based analysis of mixtures. And when we're talking about composition of a gas, in terms of why would you want to know that? In a reforming process, as another example, the process engineering or optimization team might want to say, oh, okay, I need to sample the feed. I need to sample the tail gas and the hydrogen stream itself as well. So you can see here that just getting, by utilizing this Raman analyzer, you can get BTU as a key measurement parameter for the fuel gas. You can also use the same device to determine the composition of makeup syngas, specific components, carbon monoxide, carbon dioxide, etc. So it becomes very useful. And because the device is an optical device, gives a lot of flexibility around the application for the temperature and pressure ranges as well, which is very useful in a hydrogen process. Now, because it's also an optical device, it means it's very quick and responsive, and there's also no need to flare with any sample gas being utilized. It can go back into the system. So you have, at this example here, you've got a spectrum with hydrogen on the blue line, methane, the green, the orange, and then nitrogen, the green. And at a specific time where the process has been inverted, where there was a reduction of the hydrogen concentration, you can see there on that spectrum, there was a very quick shift in terms of the composition measurement. And the good thing is that there was a 2-minute delay between when the Raman was able to display the full composition of the new stream. And in terms of performance from a traditional measurement, where you might utilize something like a mass spectrometer or another type of system, we've done some comparison in performance between a mass spectrometer and this optograph concentration measurement detector. And you can see that the green and the purple lines, the ones that are quite sharp and responsive, these are the optical sensor for the optograph, while the mass spec, which is the blue and the red lines, is very slow in comparison. So in this example, we spiked hydrogen gas into a turbine field to simulate a transient event. And you could see that the concentration was varied from 30% to 70% in about 30 seconds, which would be considered an extreme transient event in turbine applications. But the optograph was very responsive when it detected that. You can see, I'll read out the key there. So the blue line is the hydrogen concentration measured by the mass spec. The red line is the methane concentration measured by the mass spec. And then the green line there is the hydrogen concentration measured by the optograph. And the purple is the methane concentration measured by the optograph there. In terms of purity measurement as well, so the optical sensor can be utilized for purity measurement. You can see here that on the lower graph where you might have a low purity composition of the hydrogen gas, maybe 99%, you can detect nitrogen and also methane, the concentrations there as shown on the slide. And what stands in the way for operators to optimize the efficiency of their plants when using devices like this in the field? And the key thing here is traditionally heavy industry has been quite conservative in deploying new technologies from a field instrumentation point of view or an automation point of view. And some of the reasons for that might be around there's no seamless integration between suppliers, different suppliers and their different technologies. And there could be a high engineering effort and that there's a lot of expert data required to do this. So this is where we are now creating more advanced monitoring features from our field devices to enable these new insights being seamlessly integrated into an automation solution. So for example, a flow meter can now detect if the tubes are corroded, if there's coating inside, if there's cavitation, different phases, etc., rather than just determining flow from a certain application. Now that you can get these additional functions from these smart devices, or means you can bring the additional information up to your automation or control system and further optimize your hydrogen process. And to unlock this advanced maintenance capability, we use what we call smart software in the device. And this is really built on 3 pillars now. It's around diagnostics. So if there's a device in fault, you can get that information and optimize your maintenance regime. There's a verification. So if in a custody transfer application, you need to verify your meters to ensure that they are in the same specification as they were when they left our factory. That is also possible now these days. And then there's a monitoring side. So if you want to implement a more advanced preventative maintenance regime on your plant, you can do that as well with the monitoring parameters from the device. And finally, I just want to talk about the IoT ecosystem for hydrogen operators. So now with these days, with that additional information from the field devices, you can bring this up to a number of different platforms to enable optimization of your process, seamlessly integrate into different ERP systems. And that way you can actually get all that information from the field device into whichever process you want, so that you can optimize your process and bring a lot of value to your operation. Thanks very much for listening to me. And I think we can open it up to questions now, if anyone has any. All right. Yep, go for it.
Firstly, an apology, Ian. Is it on?
Yep.
I just noticed there seems to be a discrepancy between the notes I was given and what I've just seen on the template there. But anyway, my question is, and I should introduce myself, by the way, I'm Stephen Hinchliffe, Mark MacDonald. The question is, given that the different technical standards and safety standards in different jurisdictions, how do you accommodate that in the design of your equipment?
Yeah, that's a good question. So it is quite a challenge for us, because from a product development cycle, it means we have to incorporate all those regulations and all those standards into the product. So when we're creating a product, we do a bit of a market analysis to determine the market size for each portfolio for all these different standards. So for example, if we're targeting the hydrogen market, then this is where we have a look and see what standards are required. And then we do add that to the different portfolios. So targeted at each continent, for example, they might have different standards. So that's where we do add those into the device. I mean, that makes a challenge when it comes to choosing the right device for your application. Perhaps if you're like a skid manufacturer in Australia and you're exporting out to different countries, it's important to select an equipment supplier that actually has a portfolio range that addresses all those regulations to different areas of the world. Thank you.
We have time for one more question. If not, please. We are running a little behind time. May I suggest that we shorten the break slightly, but also come back at a slightly later time of 11 o'clock, if that's okay with you. And please do come back because it's going to be fun.
Hello, Andy and Tom. This is Erin from the Convention Centre. Are you both there?
Yeah, I can hear you.
Hey, Erin. How you doing?
Stand by one moment. Just having some technical issues. Sorry about that. I think I can hear you guys now.
Hey, how are you?
Hello.
Hello, can you hear me?
Yep, absolutely. I can't see either of you though. I might just need you to open your webcam. That is fine. All good. I'll just quickly brief both of you. So throughout the panel presentation, you'll need to keep your camera on throughout the whole duration and only unmute yourself when you need to speak or present. Otherwise, remain muted throughout the presentation.
Sure, no problem.
Next question is, I think, Tom, I've been told that you might be remotely presenting. So you'll be screen sharing your own presentation. Is that correct?
If I can, that's fine, yeah.
That's all right. Can I just get you to quickly practice, like pop it up on the screen share for me so we could just have a look?
Sure. You've disabled participant screen sharing, it tells me.
1 second, please. Just having a word with Brace now. He should be able to enable your screen share in just a moment.
I'll be back in 1 second, Erin.
That's all right.
You went jacket, I went tie, Andy.
Oh, us Brisbaneites, we've got to try and class it up
Bloody
somehow.
something. Yeah.
Don't we?
This is the tie I got married in.
Was it? Yeah.
Yeah.
Good stuff. Yeah, not many people wear a tie player anymore, do they?
Yeah.
Although jackets just too warm. Special occasions, eh?
It's still saying host disabled participant screen sharing, by the way, Erin.
Yeah, I'm trying to get a hold of Brace. He said he would be able to enable your screen share. Not sure where he is at the moment. Just going to get a hold of him again.
Hey, Erin, I sent some just a couple of slides through to Brace. Have you got access to those?
Yep, so our visual technician, he's got your slides at the moment, so he'll be able to pop them on when you have to present.
Cool, thanks.
That's all right.
I'm just going to go and grab some water, 2 seconds.
That's okay. I'll keep you both updated when we may be presenting.
How's the conference been going? Yeah, disappointed we've not been able to get down there for it. Obviously, with the
That's okay. I think it's been going fairly well. Yeah. There has been a bit of Q&A at the end of each panel. So yeah, be prepared if that happens as well. I'll let you know.
Yeah, good stuff. Yeah. Are you from Leader Associates or are you with the conference centre?
I'm with the convention center. I'm just like a general technician. Just been doing
sweet.
the Zoom call for the last couple of days. I have got Brace. That is great. Okay. Andy, did you want to screen share your own presentation, or you're happy with us to do that?
I'm happy with you guys to do that. Yeah, I'd need to go in and find it again.
Yeah,
so
no,
happy
that's
to do
okay.
it maybe I can just give you a heads up when I need to move the slide.
Yeah, because Brace has just let me know that he can also enable your screen share as well if you'd like.
Sorry, am I sharing at the moment?
So I believe that, yep, that's Tom's screen. Okay, yep, I can see your presentation. I'll just need you to put into presentation mode. Yeah, that's fine.
Okay, cool.
All good. Okay, so you're ready to go, Tom. I'll keep you updated when we may be beginning. Andy, did you want to go through your slides?
Yeah,
Still got a bit of time.
Yeah, see if I can get them here. Yeah, that should be good. Yeah, so I can put up my slides if you can allow me access.
Are we missing a few presenters? Are we being kept in different paddocks?
So we're currently still on a coffee break. We just went a little bit over time in the last couple of sessions. So I think we're probably going to be starting, I'm not too sure, maybe in 5 minutes, but I'll keep you updated when
Are the
I
other
find out.
panelists in real life, are they?
Yeah, they're just,
Right,
I
okay.
think they're actually in the room right now.
Okay, I can see one of them at the front actually.
Yeah.
Martin's there in the grey suit.
Oh yeah. Can I just test this, see if it works? And I just need to go to presentation. Yeah, can you see that now?
Yeah, that's perfect. Yeah, so it's up to you if you want to screen share your presentation, but you'll just have to let us know probably in the next couple of minutes so I can let the vision technician know.
All right. Yeah. Yeah, I'll do it from this side. That was fairly straightforward, wasn't it?
Yeah, no, that's okay. I'll just let our vision technician know that you'll be sharing your own content. Okay, all good. So you're happy to screen share, and so are you, Tom. That is great. All right, stand by.
How many people are there in person, Erin? Do you know?
I think she's gone.
Sorry, I'm still here. I keep getting questions asked at me. How many people did you say, was that the question?
Yes, yeah. Just interested to see, obviously Queensland people couldn't come down, but yeah, you had a decent turnout. How many are there?
Yeah, it's been almost a full conference room, to be fair. Like I can
Awesome.
show you guys the camera as well. Like, yeah, so that side's been quite full. This side's pretty packed usually. So yeah, it's been a very good conference so far.
Yeah, great
And
stuff.
how many people joining online?
That I can't tell you. I don't have access to the recording or the stream link yet. But Brace might know if you ask Brace. I think we might be beginning, just letting you guys know.
I like your background, Tom. I need to sort myself out with a background like that. It's good.
Yeah, it helps. I forget that it's there. It only works. I only do it in Zoom. I don't do it in Teams. Zoom's kind of normally reserved for presentations, it seems.
I'd like to make a start, if I may. I do appreciate that a big feature of conferences is the opportunity to network. However, in respect of time and with respect to the people who have come into the room on time, I'd like to proceed, if I may. So now we will be going to the panel session, the title of which is Identifying Pathways for Hydrogen Technologies to Achieve Commercialization. I propose to present our panel members first and then ask them each to give a short presentation on their area of interests. I will then invite questions from you guys, delegates. I have a few prepared questions myself, but I think it's really helpful if there's some interaction, not least because our panel members have put some time and effort into what they're doing, and you know, showing an interest by asking questions is, I think, just polite. There you go. That's my pitch. So without further ado, I would like to, and panel members, would you mind also just coming up and sitting up here? And then when I mention your names, you could perhaps nod or wave so we know who you are, if we don't already. We have two panel members that are joining us virtually, who may or may not be able to nod or wave, probably not. So first of all, I'd like to introduce Gabriel Henry, Director, Industry Engagement and Development of the Department of Environment, Land, Water and Planning, as we all like to say, DELWIP. Gabriel works in the energy industry to help develop a sustainable energy future. She has degrees in engineering, finance and humanities. It's a great mix. Because a theme of this has been the social element to the transformation that we're going through. Gabriel has 25 years experience across technical, commercial, financial policy and regulatory aspects of sustainable energy. She leads a team that works with sector participants to attract and establish new energy businesses in Victoria, to develop new energy sector capabilities, support emerging energy technologies and industries to manage the transition to net zero. And Gabriel contributed to the Victorian government's Renewable Hydrogen Industry Development Plan. If you haven't downloaded that yet, I would encourage you to do so. It's a real page turner. Seriously. No, it's very interesting reading. Our next panel member is Dr. Renata Lippi, instrument scientist, Australian Nuclear Science and Technology Organisation. And I did say to Dr. Lippi, when we were just having a chat earlier, that I am a founding member of the Australian branch, sorry, Queensland branch, I should say, of the Australian Nuclear Association. We don't have many members, but there's always hope. Dr. Lippi works on the construction of 2 new beam lines for high energy X-ray diffraction, the Advanced Diffraction and Scattering Beam Lines, known as ADS-1 and ADS-2, as a part of the BRIGHT project. And hopefully Dr. Lippi will explain a little bit about that. She has experience in hydrogen, carbon dioxide utilization reactions, focusing on the development and optimization of catalytic materials and evaluating their operating properties using X-ray techniques. Prior to joining ANSO, she was a postdoctoral fellow and project leader at CSIRO Energy and worked on several projects on carbon dioxide, hydrogenation, ammonia synthesis, and hydrogen utilization. Mark Forbes, CEO. Second? That's not too bad. That was a cricket score. I've got no idea what you're talking about. Mark began his career at this time. Mark began his career as a research chemist and moved into the water and membrane industries more than 30 years ago. He has held senior international positions with companies based in Australia, the UK, the USA, and has participated in hundreds of projects in the water, wastewater, food and beverage and municipal solid waste industries. He's been a director of the Australian Water Industry Alliance and is a member of the Australian Water Association and the International Water Association. Moving on now to Andy Marsland, who is with us virtually and on screen, I think. Would you like to wave, Andy? There you go. Andy has a BA in management from the University of Nottingham, very close to when I did my degree. And he joined H2Q executive leadership team in 2020. He's passionate about championing positive engagements for the advancement of the energy sector and the decarbonisation of society. Andy was head of the Stellar Energies business in 2010, and he has participated with startups, SMEs, and global energy companies. By SMEs, I think that's small and medium enterprises, and global energy companies to assist them reach their team expansion and diversity goals. A little bit about H2Q. H2Q is a Queensland hydrogen industry group. It's not for profit and committed to securing the economic, environmental, and social opportunities hydrogen offers Queensland and Australia. Moving on now to Martin. Martin Haplosel, and you're really going to have to. Was it a reasonable attempt? Okay, yeah, sorry. Is the business unit manager, transmission solutions and hydrogen for Siemens Energy. Martin has an electrical engineering degree and an MBA. He is responsible for the transmission solutions and hydrogen activities of Siemens Energy in ANZ. He promotes the opportunities for hydrogen technology through market development, government dialogue, speaking engagements, as per now, and interviews. Martin was a member of Alan Finkel's stakeholder group forming Australia's national hydrogen strategy. Martin's expertise covers hydrogen technology solutions, electrical power system applications, technologies for maintaining system strength, very much of interest to me, and stability, a business case development, automation, and energy technology business management across diverse industries, including utilities, resources, infrastructure, transportation, and manufacturing. Tom Cameron. Hey, Tom. Tom is a chartered mechanical engineer who has spent his early career in the oil, gas, petrochem industries and focuses On the future fuels and energy sectors, Tom is the Hydrogen and Chemicals Technology Director at Oricon, a role which sees him interact with a wide variety of industry participants, helping shape the future for future fuels and their opportunities. Tom has a broad experience across the full life cycle and spectrum of projects from his previous technical, project and commercial roles. His background in conventional refinery ammonia hydrogen applications provides a foundation to advise on development of green hydrogen, project concepts, supply chains, and business cases for energy transformation projects. Ladies and gentlemen, the panel. I would now like to ask each of the panel members that do have a presentation just to give a short presentation to introduce themselves further and more particularly their areas of interest. The first being Gabrielle Henry.
Thank you very much for the warm introduction, Stephen. And it's so wonderful to see you all in person today, see some familiar faces and meet some new ones. I'd like to start by acknowledging the traditional owners on the land on which we meet, the Wurundjeri people of the Kulin Nation, and pay my respects to elders past, present and emerging. Next slide, thanks. As many of you would be aware, Victoria has legislated clean energy targets, and the transition to a cleaner energy future is well underway as we move to our target of 40% renewable energy by 2025 and 50% by 2030, and ultimately legislated target of net zero emissions by 2050. So last November, the Victorian government committed $1.6 billion. So that's just over a year ago, when we've been very busy in moving towards investing that funding in our clean energy future. And increasingly, we've got to focus on renewable hydrogen. As Stephen mentioned, we released our renewable hydrogen industry development plan in February of this year. And next slide, thank you. So through the release of the plan, we've already laid the foundations and captured the momentum in the sector, with the aim of rapidly establishing Victoria as the home of renewable hydrogen. And what we're targeting includes pilots, trials, research, feasibility studies, investment attraction, building supply chain capabilities, commencing legislative and regulatory changes, and building workforce capabilities, skills and training opportunities. Just a few things on our radar. So we want to see the clean energy sector grow and strengthen, and see new skills and technologies tested and expanded, and connections made between the physical infrastructure, skills and energy resources to eventually achieve a thriving renewable hydrogen economy. Next slide, thanks. So our renewable hydrogen industry development plan sets out how the Victorian government has established foundations to support the emerging Victorian renewable hydrogen industry, and connecting sectors of our economy through renewable hydrogen will bring new jobs and investment and spur economic growth to our state. And complementing this plan, we've got supported several key initiatives in 2021, and some of them are shown on the slide there. And we recently closed our first targeted renewable hydrogen grants, and that included a fund, the Business Ready Fund, to support hydrogen trials and demonstrations, along with the Commercialisation Pathways Fund, and covering business cases and feasibility studies for businesses to transition to renewable hydrogen. We've also developed an Energy Innovation Fund, and that's an overarching $108 million program under the Energy Innovation Initiative. And that's putting substantial funding towards transformational energy projects, including renewable hydrogen under that umbrella. So announcements and outcomes of these programs are due before the end of the year. And I'll just add, we've also put support for the Victorian Higher Education State Investment Fund, and over $20 million under that has been allocated to further develop renewable hydrogen capabilities in Victorian universities, including Swinburne, Deakin and the University of Melbourne. And that will fund hydrogen research, building industry partnerships, and the demonstration and testing of hydrogen technologies and facilities. Next slide, thanks. There are opportunities for the development of various types of hubs in our regions, and we see the potential of Victoria across the whole of our state. And that's due to our integrated gas and electricity infrastructure. We've got largest gas network in the country. We've also got a comparatively high population density, and coupled with a plentiful supply of renewable energy and well-established transport, freight and export routes, including the country's busiest container port, we see that as significant advantages for Victoria for both domestic and international markets for hydrogen. So we support the collaboration across the supply chain, and that's why we're co-funding National Energy Resource Australia's regional hydrogen technology clusters in Victoria. And we've got 4 in Greater Geelong, Gippsland, Clayton and Mallee regions, and looking to add further in future. And we've also established a statewide Victorian cluster network to help coordinate across those entities. So those clusters will connect stakeholders from across research institutions, government, industry and startups around strategic regions in the state that have strong potential for hydrogen. And they will drive opportunities to collaborate, attract investment, solve industry-wide challenges and drive commercial projects. So we see Victoria as being well positioned for opportunities to build a domestic hydrogen economy, but to also create a world-class hydrogen export industry. And we're really keen to work closely with business and industry in Australia and internationally to develop domestic demand and to establish and refine the supply chain needed to support renewable hydrogen projects. So we're happy to offer tailored support to companies, including assisting with the identification of opportunities and development of business cases, engagement with potential partners, research organisations, suppliers and customers, and helping with site selection and navigating regulations. Final slide, thanks. So I hope I've just given you a bit of a brief snapshot of the state government's decarbonisation goals and its plans and projects to help build Victoria's sustainable and thriving renewable hydrogen economy. And I encourage you to reach out to me and my team to discuss projects and opportunities in the state. Thank you so much.
I would now like to ask Dr. Lippy to give her presentation.
Cool. So thanks, Stephen. It's great to be here today and tell you a bit about what we do. I'm from ANSTO, which stands for Australian Nuclear Science and Technology Organisation. And I'm just going to tell you a bit about, what can we do to help you solve some technical challenges around hydrogen technologies. Next slide, please. So ANSTO has 2 facilities which are quite relevant for hydrogen technologies. So first one is the Australian synchrotron that's based in Victoria. It is a particle accelerator, so not something that you may have in your as part of your your company. And it's based in Victoria, and it generates X-rays, really bright X-rays. In Sydney, they have a nuclear reactor, which researchers and industry can use neutrons to do R&D. So some of you will be quite disappointed that I'm not talking about pink hydrogen, and I'm sorry for that, but I think there's some really cool things that we can do with both this amazing, really bright X-rays at the synchrotron and also the neutrons that we generate through using the nuclear reactor in Sydney. So first I'll just touch on hydrogen utilization, and here I say hydrogen utilization, it's more hydrogen conversion, right? So this is my area of expertise, so catalytic conversion. As Stephen has introduced me and mentioned, I have experience in ammonia synthesis, cracking, also liquid organic hydrogen carriers such as methyl cyclohexane, for example, and also renewable hydrocarbon fuels, so synthetic methane, methanol, and etc. Now, all of these catalytic reactions, you can actually make use of X-rays and neutrons to understand your reaction better, to develop your reaction better. So it's very interesting to see, to be here at this conference and see what the market's doing. But I think most of you could tell that ammonia has been the main topic, liquid and compressed hydrogen as well. But I think there's room, although those are the low-hanging fruits, technology is really well developed. I think now is the time to start looking for what's the next thing, the next breakthrough to actually make hydrogen, especially green hydrogen, happen. And I think that a lot of this is in catalysts. So if you want to increase your efficiency of your project, decrease energy requirements, that's usually down to the catalyst for these conversion bits. And so, we can do all this in situ characterization. So I can talk to you, one-on-one or during the panel later. Also, hydrogen storage. So you can also store, and this hasn't been mentioned at this conference so far, you can store hydrogen in materials like metal hydrides and also metal organic frameworks. So new technologies, new materials, perhaps understanding this better might help, your business case or, developing that first stage of research, so you can have some performance numbers and then move on to, a business case and so on. And at ANSTO, some of those facilities, you can understand hydrogen interactions. So hydrogen is quite difficult to see using many techniques, but neutrons, you can get good scattering of neutrons and you can actually tell what hydrogen is within the structure, which is quite unique. And other storage materials, also computational investigation for new materials and so on. All of this is R&D that I think it's very important to support the green hydrogen economy moving forwards. And yeah, ANSTO does some of these things. And also other hydrogen technologies that I haven't mentioned, perhaps new materials, you're scaling up a process, you're having some issues with, I don't know, for example, corrosion and so on. And you just want to understand what's causing that, what's the source of that. And I guess some of you might use X-rays for that, but I wonder how many have used neutrons to investigate those things. So just if you think, there's not an answer for your question, it's good to reach out to researchers sometimes. I feel there's a bit of disconnect between industry and research, but yeah, we're there to help as well. Thank you.
Thank you, Dr. Lippi. Your mention about alternative carriers for hydrogen is really interesting. As I understand it, you can get quite high densities at relatively low pressures. I'd now like to invite Mark Forbes to present.
Thanks, Stephen. This will be a fairly short presentation. We are talking, or we are interested in supplying water for hydrogen production. And we believe that the most sustainable source of water is going to be municipal wastewater. On the east coast of Australia, there are already battlegrounds around every other source of water. The Artesian Basin, the Murray-Darling Basin, everybody's laying multiple claims to the little bit of water that's there, but there is wastewater available. And we can treat it to any level that electrolyser companies would like it to be treated to. And that really is our basic business model. The difference that we have is that, can I have the next slide, please? Is that we can actually derive value from the oxygen as well as from the hydrogen. About 80% of the energy consumption in a sewage plant is supplying oxygen to keep the bacteria eating the municipal waste. So if we've got a Just an example I've drawn up here, a city of 10,000 people, a small rural city about the size of Parkes in New South Wales. That needs 45 kilos of oxygen an hour, which is currently supplied by about 40 kilowatts of electricity. So there's about 350 megawatt hours of power used annually at about $70,000. That equates to roughly $1.40 per kilo of hydrogen that's produced in the same facility. Now that's a bit of a pie in the sky number, because I'm assuming that it costs you nothing to get the oxygen from the electrolyzer into the wastewater. But given that the oxygen is actually generated if you're generating with solar, the oxygen's generated at the same time of day as it's utilized by the waste facility. So storage can be minimal. There's absolutely no reason to be liquefying oxygen. You can be storing at relatively low pressures. The other interesting part about that is that by changing the technology to utilizing oxygen in a process called fixed film bioreactors, we can in fact double the capacity of a sewage plant. So if you've got a country town that's growing, that needs additional sewage capacity, we can actually achieve that in the existing infrastructure with very small capital outlay for additional diffuser systems. So putting those two things together, we see that there's a business model for having regional hydrogen plants co-located with sewage facilities. The other advantage of a sewage facility is they all have an odor buffer. So there's about 500 meters of ground around every sewage facility that's not used for anything. So you might as well park a solar farm there. Yeah, so, and all of these small towns have transportation requirements. They're all transportation hubs of some form or another, even if it's just running local wheat trucks to the rail port. And in the larger areas, I can actually envisage trains with a hydrogen carriage rather than the old coal tender from the 1800s, running up between Melbourne and Sydney, Melbourne, Brisbane, Brisbane, Sydney. So that is our vision for commercialising hydrogen in a different way to what other people are looking at. We're not looking to build massive facilities to export. That's somebody else's job, and lots of people in this room probably want to do that. But we can see a different business model where we can supply green hydrogen into an area that can utilise it. So thank you.
Thank you. That was really interesting. I'm aware of the proposal to use recycled wastewater, and I think Jacob wrote a report on that a little while ago. I wasn't aware of the benefit of using the oxygen in the wastewater treatment. That is really illuminating. I'd now like to pass on to Andy Marsland of H2Q. Andy.
Thanks, Stephen, and apologies to everyone that couldn't be there in person. Firstly, I'd like to acknowledge the traditional custodians. Here in Brisbane, it's the Yagara and the Turrbal people, and pay my respects to elders past, present, and emerging. H2Q is one of the clusters that Gabrielle mentioned before. We are a Queensland-based cluster. What I'm going to talk about today is very replicable, so I'd encourage you to perhaps reach out to one of the cluster organisations in your region and connect in with them. The clustering is fairly new in Australia. It's been around a lot longer in Europe, and the research has shown that clustered organisations are about 17% higher output than non-clustered organisations. So H2Q has been around for about 18 months, and we were officially launched from the NERA investment in March this year. So it's really around that sort of engagement, collaboration, and growth and investment. just struggling to share my screen, just one second. Yeah, so H2Q is an industry-led not-for-profit organisation. We're officially launched in March this year by Minister De Brenny, the the Queensland Minister for Hydrogen for Queensland. We incorporated as non-for-profit, got an advisory board in place, which is a cross-section of major organisations, top-tier power producers, banking, SMEs, which I think we can talk about today, and some of those technology developments coming through. And hydrogen producers. Some of the activities that H2Q has participated on so far. So early on, we established a need for the supply chain mapping or ecosystem mapping. So H2Q launched, we engaged with a company called Economics to identify who was doing what in the industry. NERA have then taken that and run with that nationally. It's become high capability. So I'd suggest checking that out. It's a great platform for organizations to showcase their hydrogen capabilities. It's free to put a profile on there, and that's able to be accessed from people in Australia and also international organizations looking in on Australia to see who does what and the search functionality behind that. We've also got participation in the Queensland Hydrogen Task Force. So Renata, who's the chair of H2Q, also sits on the government's Hydrogen Task Force. We've got monthly newsletters that go out to our member base. There's a roadshow. So far we've been to Cairns, Bundaberg, Mackay, Mount Isa, had a number of workshops in the Brisbane region as well. One of the things about clustering as well is to bring in all different parties from different areas. And what we're seeing, particularly in the workshops with the technology advancements, is that it's a really good kind of gene pool of different skills coming together. So you might have people from the solar industry or the wind industry or land access, or people that have got knowledge of policy developments. We've got universities involved. The QUT, Griffith, and University of Queensland have all been heavily involved, and we've got a couple of working groups who meet up on a regular basis to overcome some of the challenges that we see ahead in the industry. And finally, yeah, as a side project, we've recently launched the Exploring Hydrogen podcast. So yeah, feel free to check that out. It's on Apple and iTunes. Google Play, and there's a number of organizations that we've interviewed to see where they're going as companies, and again to share that message. What is hydrogen? This is to the broader community. I think one of the things that we can do as an industry group or as collective clusters is to spread that word about where the industry is going. So yeah, thanks very much for your time, and look forward to having some questions from the floor.
And finally, I'd like Tom Cameron to give a brief presentation. Tom, I think you're muted.
There we are. Once I shared it, moved the mute button. Apologies for that. And as for Andy, apologies for not being there in person. So I'm aware that we're pretty behind time, so I'll skip as fast as I can. So I've already been introduced. Generally speaking, Tom Cameron, live in Brisbane, been involved in oil and gas and petrochem for my entire career. I'm Oricon's Hydrogen and Chemical Technology Director, and what that means in real terms is I get to play with all the fun things at the moment. So anything to do with the hydrogen focus or future fuels or derivative chemicals, I typically get to play and get involved. Mechanical engineer by training, but realistically don't spend a great deal of time crunching numbers anymore. Most of what I do is looking at the sort of high level 30,000 foot view of supply chains and flow sheets and whole whole business concepts, I guess. And while we do get to play a little bit more now in the execution phase as things are becoming more real, a lot of it is in that conceptual level still. So when we consider a supply chain as a system and we're the system designers, we need to grapple with the demands of the downstream, the constraints of the upstream, and the economics of the production. As a designer, we have a number of different tools at our disposal. Fundamentally, we're trying to generate power to produce hydrogen, to then use hydrogen. And this can be viewed as energy flow through different carriers. We can move energy as electricity. We can move energy as hydrogen molecules. We can also store energy as electrons and molecules. Our molecules can be stored or moved as a liquid. Our molecules can be stored or moved as a liquid or a gas at a variety of pressures. We can design flexible or bespoke downstream plants, or we can take the constraints of a brownfield plant as a given. We can oversize generation. We can oversize hydrogen production. We can constrain or unconstrain our electrolysis technology. We can even use commercial instruments such as PPAs to buy firm renewables. So as an example of a supply chain represented as a cost stack, here's green ammonia from generation to loaded onto a ship. You can see even as a derivative product of hydrogen, it still sees its largest cost contribution as renewable energy. And this stack is based on some reasonably optimistic levelized cost of electricity from say 2030 onwards, and it's still pretty challenging. However, there are a few applications for ammonia, just as there is for hydrogen, where the increased costs won't have a significant bearing on the price of the finished product. And likewise, some cases, just like hydrogen, represents the only credible pathway to zero emissions. So this slide's meant to depict the kind of analysis we can do as a designer to optimize the system. This is a typical generation profile where we've combined wind and a solar trace. I can't remember exactly why, but it's got a battery in there, but you can see at scale, the battery doesn't add a great deal to the story. So the question is, how large of an electrolyzer can this generation support? 150 megawatts, 175, and so on and so on. And it becomes the choice of the designer to figure out where best to right size the variety of different components within the system. And as an example, in the chart, there are some of the metrics that we might look at: the utilization of the electrolysis, the total production of hydrogen over a time period of a year, and ultimately the spilled energy, because that all adds to the cost of the full system. So what happens if you test one of the constraints of the electrolysis? So this first chart, or the first table in green, is at 100% nameplate. And we might need to speak to Martin about the technical implications of what I'm about to say. But what happens if you release the constraint of 100% nameplate, made it 110, and allowed the electrolyzer to ramp up beyond its nameplate in certain instances when the power is available? And you can see for spending very little other capex, perhaps more opex, but the production of the system changes. And I guess that's what it's all about, is trying to find the best combination of technologies to try and build your system to provide the best, most practical product for the application. And I just wanted to show you a different view on the commerciality rather than at an equipment level, but just as a full system and supply chain level. And that's it. I'll look forward to hearing from you all.
Thank you. And we are a little pressed for time. But I would, oh, sorry. I was just going to cut you out, mate, because we're too short of time. Please, Martin.
Good morning, everyone, and thanks for the opportunity to speak to you all. So representing Siemens Energy, we're a PEM electrolyzer manufacturer, amongst other activities in the hydrogen space, both blue and green. PEM, proton exchange membrane. That'd be another topic to talk about, the differences and advantages of PEM versus alkaline and other emerging electrolysis technologies. But today's panel is talking more about commercialization topics, and there are some common themes to those which were mentioned by Philip and Karen, coming at it from the alkaline electrolyzer point of view, that I'd like to share. What is Siemens Energy as an electrolyzer manufacturer doing to help progress the commercialization cause for the kinds of projects which we've been discussing over the past few days? So the first point I'd like to make is designing for scale. So unlike other systems, people often see something like a battery solution and they see rows upon rows of containers and say, well, you can simply scale up by deploying multiple containers. But actually that won't be your most cost-effective method to scale up hydrogen. So if you have a hydrogen electrolyzer and the water treatment and the cooling and the gas compression all at subscale and then multiplied many times, that will not bring your best economic outcomes. Indeed, you have to design from scale. And in that sense, our modular array shown there is sized at 17.5 megawatts. And with that size, it's actually quite easy to imagine a 100 megawatt project. That's only 6 of those units together. And as illustrated there, you simply design them side by side to get to those scale numbers that we're talking about in the next waves of projects that we need to deploy in this country. The second point or contribution that I'd like to share is the pre-engineering to accelerate the time to market, because deploying electrolyzers individually and then bespoke engineering the interfaces every time, again and again for a project, adds time and cost. What's shown there is it's more than just a 3D model. It's actually a digital twin. So it's actually a working 3D. The intent being that once it's in service, it allows you to monitor the performance and optimize how it's operation. Now, we're not quite there yet, but so the first value we're going to get from the pre-engineering is the interconnecting piping, for example. So for us, the system is the rectifier transformer, the rectifier, the electrolyzer itself, the water polishing and recirculation units, the oxygen, hydrogen collectors and cooling circuits, and all that can be pre-engineered. The pipes as shown there, pre-produced, and then accelerates your deployment. And the third contribution that I'd like to mention is the automation. What's shown there is a robotic manufacturing of the stack. So we put this in service last year, and not only does it increase the speed of production, but also the quality that we need to achieve at scale. That's it. Good. Thanks very much.
Thank you, Martin. Last but by no means least, we are a little behind schedule, but I'd like to have 5 to 10 minute questions for our panel members. If you do have a question, please do come up to the microphone, state your name and affiliation, and obviously the question.
Hi, I'm Claire Shepherd from Worley. Just for Martin, we have some concerns over the supply chain for materials for electrolyzers, especially when we're talking about multiple tens of gigawatts of scale, and particularly platinum group metals. The supply chain's just not there. I'd be interested to hear what you have to say. Thanks.
Yeah, thanks, Claire. Yeah, no, that's a recognised challenge. And if you looked at the iridium price and how that's developed in the last year, and there was kind of a 6-fold increase where everyone's expecting electrolyzer costs to come down, and with the precious metals content, of course, that kind of pushes it in the other direction, cancelling out the automation. I think what's being produced today does not represent the status of the technology that we're going to deploy at scale in time. And we strongly advocate that the industry needs to get rolling. And once we start deploying at scale, further investments go into the R&D. In fact, there's a lot of research development going on to reducing the precious metal contact and alternatives as the catalyst. And I think, if we look back at the earliest wind turbines or the earliest solar panels, and you look at where the technology is today, huge advancements, and that's what you see once you get a rolling industry and the reinvestment of the R&D and then deploying at scale. So no, I do agree, it's a valid point. But I think that's not a reason that you shouldn't start on a journey in one direction. Indeed, you have to have faith in the system for further improvements, just like we see in all new technologies.
Thank you. Yes, please. And also, please indicate which panelists you'd like to address.
Yes,
the question.
Naushad Haq from CSR, and question to Martin. Martin, with PGM, are you designing the electrolyzer thinking about how easily the PGM can be recycled from the system, or not only PGM, other metals, so that recycling may have some implication in the downstream? And are you aware of anyone working deeply into that area?
No, we are conscious of that. I think a company like ours has to think, cradle to grave in terms of the products that we produce and we put out into the market. So together with the development of the products, we also have a refurbishment program where the core electrolyzer technology has a design life of 20-25 years, like any industrial plant, and if you look after it, it'll last as long as it does with control systems upgrades. But it's the stacks themselves, and you're right, and stripping out the raw materials, including the precious metals, pulling all that back out again, and reusing them, repurposing, refurbishing the stack. The end plates are eminently reusable. Probably by the time that happens, given that you have a 80,000 sort of hour life of those with the next generation. So that is front of mind for us in the concept of the design.
Thank you.
All right, so Darren Jarvis from Incitec Pivot. Really a question for any of the panel members. We're really in the heart of a classic first mover disadvantage situation. There is a lot of expectation that hydrogen manufacturing cost will go down, supply chain cost will go down. So how do the panel members see first mover disadvantage being handled, particularly in this development of new and improved technologies?
Gabrielle, I should go first.
I'll be very happy to respond to that one. Sweet. So Victorian government, we're providing support, recognising some of these early mover, as you say, disadvantages, recently through our funding rounds. That's one way to help overcome some of those barriers. But I think you've also got to recognise it's not, yes, there is a first mover disadvantage in terms of upfront cost. But for some organisations or businesses, really getting in early in what's a very rapidly evolving international market is sure to bear significant advantages. If you can get your name on the posters in the early stages saying, you're some of the early companies sort of to do this, I think there's really a very rapidly evolving market, at least internationally. And we've had a number of international jurisdictions stating publicly stating their ambitions for the importation of renewable hydrogen, if you're interested in that part of the market. But the Victorian government does recognise that, we need to provide some support in the early stages while commercialisation develops. And that also includes our support of the clusters, as I mentioned, so that we can get, industry and businesses, universities, governments working together to overcome some of those challenges, and also increase some of the demand, because the more we drive demand, the more we're going to be driving down the cost of supply.
Thank you. I might have some additions to that, Darren. I think that's a really fair point. That's a disadvantage. And I think it is right and proper to subsidise the initial projects to, some might say, obscene amounts. You might say, well, the amount of capital cost subsidy that's being offered here, why would you do that? And the reason you would do that is because everybody else benefits. I say to people, it's not the passing of time that will reduce the deployment costs of electrolyzers. It's the practical experience we gain. Same with the solar, large-scale solar. It wasn't just the reduction of the price of the solar panels, it was the methods and the techniques, tools, and way we deployed it that helped drive those costs out. And it's that experience we need to get a hand on. So very generous subsidies when you think about the big prize for the Australian society to be successful. The prize is enormous. This is our next major export substitution after the fossil exports. That's the prize. And therefore the investment we make here, just like we make investments in roads and other infrastructure that helps industry benefit society, is a valid pursuit. And I think that first mover disadvantages has to be overcome with generous, maybe obscenely generous, because we all stand to benefit from that.
Thank you. Dr. Lipping, would you like to comment?
I don't think I have much experience in this area, but I feel like, yeah, there's this a disadvantage of starting, but then I feel like, yeah, it's a big risk, but perhaps big rewards. Is just weighing that and saying, like, I think it was mentioned, having your brand associated with, being one of the first people in this area. And I think you can think of, just a very, general example. Think of electric cars, you think of Tesla, although there are all these other brands now, car makers making, but, so would that be an advantage for your brand? I'm not sure, I can't comment on that, but I think that, yeah, there is disadvantage, but maybe some rewards in there.
May I ask a follow-on question before I move on to Tom and Andy? How do you see researchers like yourself being able to work with industry and vice versa to address some of those technical issues that are identified as we start to roll out the technologies?
Yeah, so absolutely. So once you start, there'll be issues. I mean, yeah, it's just the reality of things. So you have a plan, so, whenever you're scaling up, even if it's different modules, there will be integration issues, there will be challenges in R&D. And I think, reaching out to experts, perhaps, academics who have already modeled some of these things, or, even have a bit of a blue sky idea. And again, it's about risks. So if you're willing to sum the risks of being the first one and, trying a new technology and so on, I think it's, again, it's, it comes down to perhaps there, it could be big rewards in there. And I think with support from, as it was mentioned, perhaps some grants and things, minimizing some of these costs, and maybe that risk is worth it. And I think, it's hard to put a number into environmental costs, but I think we should start putting some numbers in that, and just, making those equations actually make sense from an environmental point of view, and not just market, but yeah.
And Mark?
For one who's putting their hand in their pocket to be an early player in this market, my very best friends are sitting right next to me here, and several who look like are at the Fed blend. And the real key is the ownership of the IP. And that's what we really have to be careful of, particularly when you've got multiple organisations, as we do in a project that we're proposing at the moment. So the ownership of the IP it's not just what you can write in a patent, but it's what you have learnt that you can then exploit that to actually create a market advantage for yourself. So we realise that government funding comes with a requirement to spread the knowledge, but that's got to be limited to some extent, that we can actually, because we're putting our hand in our pocket as deeply as the government are, we have to actually get the commercial benefit from where we're going.
Thank you. And Andy, would you like to respond to the question? You're frozen, mate. Well, not you, the technology.
Starting to see some of the organisations who've been, I guess, driving the change and driving the industry forward, starting to see the benefit. I do take the question as comment, though, that there is potential disadvantage, and so continuation of the funding and support from the government to get through that, I guess, what can be described as a bit of a valley of death, particularly for smaller organisations to get them up and running. And with regards to IP, we're trying to create a framework that is open to engage in collaboration and help each other out. But yeah, I do recognise that there's a kind of fine line between sharing too much IP. So it's something that we're working through as a group, and I'm sure all the other clusters are the same, but we're finding that organisations who are actively involved and actively participate and share as much as possible are gaining the advantage.
Thank you, Andy. And I think there's some published material which demonstrates that those companies that do collaborate tend to be more profitable in the long run. Tom?
I'll try to be brief. I think, Darren, excellent question. One of those few ways I can try to answer it would be perhaps looking at the export scale and the export market. And two sort of early mover advantages I can think of might be one, and I appreciate that the development and design of the commercial instrument will be the challenge that can account for future costs and prices, but getting the hold of that first customer, I think, will be important in the export market, and particularly as the market is relatively shallow, if you can get your hands on those first international customers, and relationships will tend to stick, I would suspect, from that initial engagement, and you might open yourself up to an advantage for future sales as that market grows. And the second one, I guess, would be, again, more relevant at the export scale, and that's where, as I mentioned in my brief, that energy is the key and cheap energy is the key. So if you can get your hands on some of the better resources, which will eventually be also harder to get your hands on, so there could be an advantage to be had by having access to the best, cheapest, most coincident renewable energy.
Thank you. And if I may, I have a couple of fairly direct questions directed at particular individuals, questions. And Mark, I was really intrigued by what you said about oxygen and the use of that byproduct. How can you promote that to the industry?
Well, we're going to build a demonstration facility. We're on a small scale where industry will be able to see it operate. We'll be able to quantify a lot of the numbers. And the next stage would be to look to a larger demonstration. Because it's the municipal sewerage industry that we're talking about, that is one of the things that you can never shut down. So you can never take the risk of actually closing down a sewage treatment plant. You can't say to everybody in Wagga Wagga, sorry guys, you can't flush for a week. You know, that's just not going to happen. So the industry is very risk adverse. And I've spent 30 years introducing new technologies into the municipal water and wastewater industry. So we have a plan to do that, but it's going to be quite a challenge to actually get an uptake without us being able to provide two technologies operating at the same time. So, for example, we wouldn't take out the existing infrastructure. We'd put ours in, and if they had a problem, they can just turn the old one back on. So that's the sort of thing that we need to be able to do. And once we've done the demonstration, we'll be, seeking cooperative municipalities.
Excellent, thank you. And I have two last questions, one for Dr. Lippi and one for Gabrielle. Gabrielle first. I went through the hydrogen roadmap and I noticed it didn't really talk about sequestration. Yeah, I am aware that there's been quite a few wells drilled in the Latrobe Valley looking at the prospectivity for sequestration. Could you say why that wasn't included in the roadmap?
Thanks, and it is an important point of clarification, and I didn't mention in my introduction as well, but the Victorian Renewable Hydrogen Industry Development Plan specifically focuses on renewable hydrogen, and I'll get into why in a minute, but it is really complementary to other forms of hydrogen production, and it's both sort of informed by and complements the activities, policies, and initiatives associated with that. You will be aware that there is a major and world-leading project in the Latrobe Valley, the Hydrogen Energy Supply Chain Project, and the Victorian government, in collaboration with the Commonwealth government, Japanese government, and an entire consortium of partners, have put significant investment into that to prove the generation of hydrogen from brown coal coupled with carbon sequestration to produce that form of clean coal. Now, that investment in that project is already well underway. In fact, in January, we're expecting the arrival of the ship that will take liquefied hydrogen to Japan as a, sort of as a world first proof of concept. Now, that is already sort of essentially we're seeing we've got runs on the ground. Now, one of the things about coal is that you're not going to dig up coal in lots of different places around the state. You pretty much know where your accessible coal reserves are associated with existing mining facilities. Renewable hydrogen, on the other hand, can really be produced in small or large quantities at almost anywhere in the state where you can connect into renewable energy and you have a source of water. So that's a much more complex picture, and therefore that's why we wanted to focus on the potential for renewable hydrogen. Also, with our targets in mind of renewable energy out to 2030 and our net zero emissions out to 2050, really looking at that pure and clean generation of hydrogen sources. The other thing to note is obviously there's hydrogen production, and then there's hydrogen transport and storage, and then there's hydrogen use. Now, once you've produced it, the molecules are pretty agnostic about where they've come from. They're all treated exactly the same when you transport it and store it and use it. So a lot of the things that we're covering as part of our industry development plan are common regardless of the source of hydrogen. But we just focus on that particular aspect of hydrogen production because it has some particular complexities around it that we want to get on board with and explore early on. But everything else in terms of making sure that we've got training, we've got safety covered, we've got all the standards, regulations, and all of those foundational activities we need to be able to do things across the state in combination with our clusters, which are really focusing on the benefits of different types of hydrogen production around the state. We then have a comprehensive picture for hydrogen production and use in the state.
In short, an integrated plan.
Absolutely.
Thank you. I always wonder if you mix green hydrogen and blue hydrogen, do you end up with tartan hydrogen? But anyway, Dr. Lippy, I'd like to, you talked about catalysts. Could you just elaborate a little bit about that and how you see novel developments of catalysts improving the efficiency of electrolyzers?
Sure. So I guess I'll change a bit my answer actually. So I won't talk about electrolyzers, but I'll talk about catalysts. Yeah.
Technologies.
So obviously, there's been consideration of using ammonia synthesis and cracking at the end. Cracking still a bit of the issue. Synthesis is well established through the Haber-Bosch process, cracking not so much. I'll add to that I think part of the problem with cracking is also separation. So you need to separate ammonia that hasn't been converted back into hydrogen from hydrogen, and that can be a bit of an issue sometimes, depending on the purity you need. That's one thing. I did mention, other hydrogen carriers. So MCH has been mentioned. That's not the only molecule that you could transport hydrogen around. So basically, with MCH, so methyl cyclohexane, you have your hydrogen, convert that into a molecule that's liquid at room temperature. You can transport in the same or kind of very similarly to petrol. At the end, you dehydrogenate to recover that hydrogen and send the bulk of the rest of the molecule back for recharge of hydrogen. That's one thing. But also, I feel like petrol is not just being used for energy. There's all this chemical industry. So, and that needs to be replaced if we move away completely from fossil carbon. And there has been some really fast developments in the area of CO2 capture from air. And the economics starting to make sense. 10 years ago, there was a ridiculous idea, and now it's actually, well, maybe we can try some things. And I get that maybe you don't want to get CO2 from air and react that with expensive green hydrogen and make methane to burn, because it wouldn't make sense. But even thinking, can you use that hydrogen that both green hydrogen and CO2 from air, expensive molecules to make? Maybe you can start thinking of pharmaceutical industry. Is there any, can you start making fancy molecules with that? So that sort of utilization, maybe, yeah, it is an expensive molecule, but maybe you can add value and then make the economic sense, small scale, but that needs to be mainstream as we go on with the hydrogen economy. catalysts do have a role in playing for blue hydrogen, but I think we really should, you know, at the research level, we should be thinking of green hydrogen. I don't think we should perhaps solving industry, you know, problems at this stage, but perhaps not creating new technologies based on blue hydrogen, because I feel like green hydrogen is the way to go. We have all this solar energy, because wind energy is also comes from solar somehow. So all that solar energy available, and we should really harvest that to make the most out of, you know, preserve our planet, and also have all the tech, you know, the things that we like, the medicines and so on. So yeah, catalysts are very important materials, and you know, all chemical processes currently, I think 80% of all chemical processes have a catalytic step. So they're overseeing. People don't like to change processes, but if you can optimize catalysts, if you can optimize your whole process.
Because could we say that catalysts are cool?
They're cool. They're
They're
awesome.
Cool. I'd like you to thank our panel, both here and virtually, please. Thank you. Now I'm going to ask you guys to vote, because I realise that I'm between, in my closing remarks, I'm between you and a flight, or a cold beer, or a glass of wine, or a gin and tonic. Are we too early for a gin and tonic? No, not really. So I can either do this. I can either give my full 10-minute wrap-up speech, I can give a 5-minute speech, or I can go straight to the joke. So who wants a 10-minute speech? 1, 2, 3, 4, 5. Okay. Who wants 6? Who wants the 5-minute talk? 1, 2, 3, 4, 5, 6. Okay. 7. And who would like me to go straight to the joke? 1, 2, 3, 4, 5, 6, 7, 8. 1 for 50. Okay. Right. You didn't hear that, did you? So right. Okay. Look, it's been a great. I'm not going to go straight to the joke. It's been a great conference. Absolutely great conference. And I really do want to thank the organisers, Lead Associate, for putting on such a comprehensive conference, inviting such good speakers, and indeed yourself, the delegates. So would you please join me in giving a round of applause? I've been impressed by the enthusiasm, the pragmatism, the talk about the social license to operate, different energy vectors and how they're end use dependent, the cost of fertilizer and the need to consider the poor, government support and the options to divert fossil fuel subsidies. Who would have thought? The need for legislation and regulation harmony, the taking little steps suggestion. You know, let's do a few 10 megawatt projects before we go to gigawatts. We've talked about some of the energy and market risk and transmission risks. And I often hear people talk about, oh, we can make use of negative energy prices in the pool. Well, you can until we get a lot of load. And then guess what? Those negative prices are going to go away. We've talked about the need for a holistic approach and demand side measures. And as an old physics master of mine used to say, it's all connected. It's all part of one big enterprise. I've been really impressed by the vibe, the enthusiasm, and entrepreneurial spirit. A little word of caution. I was involved in the geothermal bubble in Australia, and we do really need to avoid the mistakes that were made there. On geothermal, of which I'm a great advocate, by the way, I do think, and we haven't talked about that, I think it was mentioned once, I do think that potential for hot sedimentary aquifer geothermal could be a good base load energy supply for hydrogen and green hydrogen. Now, some of you are aware there is an organic Rankine cycle hot sedimentary aquifer plant working in Birdsville in Australia, 75 kilowatts running at 98 degrees C, basically powers a pub for the cold beer. But where was that plant built in 1980? It was built by the Alice Springs Engineering Company. Now there's entrepreneurialism for you. They would never have done it before, they've never done it since, but they built it and it's still working. That's fantastic. So we need to be entrepreneurial, we need to be pragmatic. And as the Romans would say, make haste slowly, or festina lente. If we're passionate, we can have fun. I'm a great advocate of having fun. Very important. Not least for disseminating information. If you make it fun, people get involved. Now, my team know me for a number of things, one of which is telling dad jokes, which are quite often received by groans. But anyway, I'm going to finish on a dad joke and a thought, if I may. Two hydrogen atoms walk out of a pub. One said to the other, hang on, I think I've left my electron behind in there. The other said, are you sure? The first said, yeah, I'm positive. So let's lose a few electrons and become positive. Thank you.
Thanks, Stephen. Okay, this is pretty much all about today's session about hydrogen. And here I would like to sincerely post my appreciation for all the sponsors, guest participants, and support from our speakers and our chairperson, Mr. Stephen. It is your significant support that makes us possible to organize such informative and insightful program. And I believe Leader Associate will create more and more very good events or energy summits. And actually, I started my renewable journey since I finished my master's degree at the University of Queensland. And I first step, I do the rooftop solar. Then I work for a utility scale solar farm developer. And I realized that the grid connection is really challenging for the energy transition. So I go back to the study at the UNSW to pursue my PhD study as a grid connection engineer. And then I develop solar farms and I develop battery storage. And then later on, I looking at the EV car chargers, a lot of stuff. And then now finally I settled with the hydrogen. Hydrogen, which is the obviously the game changer, which cover all the sectors, including transportation, electricity, agriculture, and like buildings, those type of things. I think last but not least, thank you for all of you because you are on the very right track. And congratulations, and your contribution and the commitment is really meaningful for the energy transition. Okay, everybody, if I won't see you before Christmas, Merry Christmas and have a good holiday and Happy New Year. And we will see you probably next year. Thank you.